morning, everyone. Welcome to the second day of National Training Workshop on Atmospheric Aerosol Instrumentation. Today we will have 3 lectures, followed by instrument demonstration and hands-on session. The first lecture will be delivered by Ms. Mariam from BARC. Ms. Mariam is having more than 10 years of experience in aerosol instrumentation. Her research focuses on aerosol charge studies, hygroscopicity, and iodine aerosol. Please welcome Ms.
Thank you for your introduction. Good morning, everybody. So today we will see about the electrical behavior of the aerosol particles. Yesterday we saw so many properties of the aerosols like like the size, the shape, etc. So out of them we will start the focus on the electrical properties. So we all know that there are many properties which decides the aerosol dynamics, its deposition, its evolution, and the growth, etc. The properties are particle size, shape, concentration, composition, and charge. Among these, charge is little complicated to measure, hence many a times ignored. Even though the charge is very important, has an impact on the sampling and transportation of the aerosols inside the tubing, and the deposition inside the lungs and the pipes is also governed, or it's also impacted by the charge carried by the aerosol particles. There are many instruments available which have utilized the charge properties. Then the charge properties have been utilized in the drug delivery to increase the efficiency. They have been used to mitigate the pollution as a air mitigator. And then the efficiency of different filters, even your N95 mask has been increased by the utilization of the charge properties. So in this presentation, we will start with some basics. Then we will see the various mechanisms by which the aerosols particles are charged, and then how these charge properties have been utilized or exploited to develop the instrumentation for the aerosol measurement. So starting with the basics. So these are some of the basic equations known to all of you, I hope. So the fundamental equations is the Coulomb's law, which tells you the force, electrostatic force between the two charged particles given by this equation. Then we have the equations for the electric field, which is basically charge experience, the force experience per unit charge. And then if we rearrange this equation, we will get the force equation in terms of electric field, which is force equal to QE. So this is the basic equation which is used for the aerosol properties or the aerosol charge or the force acted upon it. Then we have another term, which is the potential difference of voltage, which again can be linked by electric field and force by using this equation. So now we will see some basic geometry, that how the electric field will be, distributed in that geometry, and then we will extrapolate that to for the aerosol transportation. So these are the two basic geometry. One is the parallel plate. So I hope all these things are known to everybody. I am just recapping or revising the basic equations so that you can build upon the things which are upcoming in the slides. So for the parallel plate, the electric field between the two opposite charge will be given by this equation, which is very simple, and the electrostatic force is uniform between the plates. Then we have the cylindrical geometry. This type of geometry is utilized in, for example, SMPS DMA. So in this, we have a cylinder tube and a wire or the small annular structure, and the electric field is given by this equation. So this equation tells you that the field will be maximum at the wire because it is having the inverse relation with R. So as your R will tends to 0, your electric field will become infinity. So if you remember the corona charger, the needles are always kept very thin to maximize the electric field. So now we will first see how this what will happen if you place electrically charged particle in this parallel plate, because it is easy to understand. So we know that the electrostatic force is greater than the gravitational force, and the transportation of a charged particle in field will decide many properties like the filtration, the collection efficiency, and it's utilized, as I said, in the many instruments. So what will happen if you will place a particle, dust particle, or say the aerosol particle between the parallel plate? So suppose your particle is having a positive charge. So what will happen? It will go towards the negative plate because there are two plates, one with the negative polarity and other is with the positive polarity. So the electric field will be towards upside, okay, and the gravity will pull it down. So there will be a stage or where there will be equilibrium, or we can consider an equilibrium state in that where the electrical force is equal to the drag force. So if you equate these two equations, so your force, the FD, that is a drag force, which you all have studied yesterday. So if we equate the electrical force with the drag force, we will get the electrical terminal velocity, just equivalent to the settling velocity, when we equate gravity with the drag force. So here we are equating the drag force with the electrical force. We get the electrical terminal velocity, and we have defined a new term, which is the electrical mobility. Basically, the terminal settling velocity because of electric field per unit electric field. So if you see this equation, the electrical mobility depends on two terms. One is the charge and other is the diameter or the size. So as you increase the charge, more will be the mobility, and the inverse relation is with the size. So larger particle will have lower mobility. So now we will see an example for same arrangement to have a feel of the numbers for the settling velocity and the electrical velocity. So it's considered a 0.6 micron particle with having the 40 excess electron charge, which has been placed between the two parallel plates. One is at the plus 1000 volt and the other is at minus 1 kV. And they're separated by 1 centimeter. We are trying to compare the settling velocity due to the gravity and the velocity due to the electrical forces. So if we calculate the Z, which is our electrical mobility, and from there we can find the terminal velocity as we saw in the previous slide. So it will come out around 0.016 meter per second. And when we calculate the settling velocity, the ratio between the two is roughly 1000. So that means the electrical settling velocity is 1000 times larger than the settling velocity due to the gravity. Okay. So these concepts have been utilized in the past by many researchers to solve different problems. So one of this example is Millikan oil drop experiment. So what they did in this, that using this similar principle which we just discussed, they tried to determine the charge of an individual electron. So how did they do that? So they took a chamber. In that they placed the two parallel plate, applied voltage across that, and there is a hole in the upper plate. If you see, in that they generated the oil droplet using the atomizer. So basically aerosol droplet, and there is a hole from where the particle will drop down. So they did it in two steps. In one step, they did not apply any field. So what will happen? The particle will fall because of its gravity. Okay, and from the settling velocity, the equations are well known. you can relate the velocity with the diameter. So using a microscope or a viewing window, they measure the settling velocity, and from the known settling velocity, they could get the diameter of the droplet. So your diameter is known from the first step when you did the experiment without the applied electric field. In the second step, they applied the field, and then they used the same equation, equating the electric field with the gravity. And from this equation, now since the diameter has been determined in the first step, you can find the charge. Okay, so using this simple principle, this experiment gave the charge of the electron. So next, this completes the basic premises of the physics for for this electrical behavior. So now we will see a few effects of charge, the application. So one is the effect of charge on the coagulation dynamics. So what is coagulation? Coagulation is basically collision of the two particles. When they collide, they stick, and because of their addition, what will happen? The size will increase and the concentration will decrease. So this charge on the particle will affect the coagulation also. So if the particles are of the opposite charge, they will repel each other and decrease the coagulation. And if they are of the similar charge, they will attract and will increase the coagulation rate. Then second effect is the effect on deposition. So the deposition on maybe pipe or even inside our lungs. So when a particle travel in a tube, maybe the sampling tube or the respiratory tube, so it can have two types of effect, which will have an impact on the deposition dynamic. The first effect is the image charge effect. So when a particle passes through a conducting surface, it will impart a opposite polarity image charge. And because of that opposite polarity image charge, there will be attraction. And that attraction will increase the deposition. So electrostatic attraction, because of the image charge effect, increasing the deposition. Then second effect is the space charge effect. So because of the high concentration of the charged particle, there will be a repulsion. And these particles are traveling inside a tube or inside a respiratory tract. So because of the repulsion, they will get impacted on the tube or the tract, and that will result in the deposition. So because of both of these processes, you will have the deposition, increased deposition inside a tube. So now we have seen some basics. Moving on to the charging mechanism. So how the different particles, the aerosol particles which you generate or which you see in your surrounding, they are getting or they are acquiring the charges. So these are some of the basic mechanism. So we will see few of them in details. So first one is the diffusion charging. In this, the aerosol particles, they collide with the ions. Those ions might be in the atmosphere, like right now, there are many ions in the atmosphere. Or you may artificially create the ions and impart or bombard those ions with the aerosols. So when they are ions, and the ions have the Brownian motion. So because of the Brownian motion, there will be a collision between the ions and the aerosol particle, which will lead to the charging of the particles. And this process doesn't require any electric field. So that is the diffusion charging. Then second is the field charging. Here also the collision will happen, but the source will be the electric field. So that is the basic difference between the diffusion charging and the field charging. Field charging is in presence of electric field only. Then we have a flame charging. In this, because of the high temperature, your ions will be generated because of ionization, and those ions will again lead to the charging. Then we have static electrification. In this static electrification, there is a separation of charges or separation of two surfaces. So when a particle is being separated from the bulk surface, That is static electrification. But there are many phases. So we have subdivided static electrification into again 3 parts. One is electrolytic charging. In this, the separation of liquid is from the solid surfaces. Then we have the spray charging, where the liquid surface is separated from the liquid surface, liquid bulk. For example, atomizer. So when you atomize or nebulize a solution, what happens? There is a bulk liquid. From there, you are separating a layer. So that is separation of two liquid surfaces, leading to the disruption and and forming the charges. Again, we will see this in detail. Then we have contact charging. So this is simple rubbing of two like woolen cloth or scale with the paper. So you are transferring between the two solid surfaces, or you are separating the powder, maybe powder from a solid surface. So solid from solid. So now we will compare again the diffusion and the field charging in details. So as I discussed, the diffusion is because of the Brownian motion of the ions, and the field charging is because of the applied electric field. So for both, we can determine the number of charges it produces given by these two equations. So from these two equations, the main takeaway is the dependence on the diameter. So if you see the first equation, in this your number of charge acquired, it is proportional to diameter. And in the second equation, the dependence is on dp square. dp is your diameter. That means surface area dependent. So your field charging is directly proportional to diameter, and this field charging is surface area dependent because of dp square relation. Also, the diffusion charging is dominant for the small size particle, but obvious because you're depending on the Brownian motion. The smaller the charge size, the more will be the Brownian motion and the chances of the collision. So for less than 100 nanometer particle, this diffusion charging is very dominant, and field charging is dominant or the very significant after 1 micron. So few examples which we can think of in our lab. Neutralizer, which we use to neutralize particle, is an example of diffusion charging. Then we have corona charger, which is an example of field charging. In both the cases, you can have the unipolar ions or the bipolar ions, or hence the particle. So most in our lab, mostly we deal with the bipolar charger because we use those only in our day-to-day lab experiments. So we will now see the distribution, like that for SMPS, like sir was discussing yesterday, in SMPS we know the distribution. So there must be some theory for determination for that. So now we will see how few of those theories. So one theory is the Boltzmann distribution of bipolar charge distribution. So now we are having the bipolar charge distribution charges in some location. So what was proposed, that these charging, the diffusion charging, is because of the collision with the ions. What are these ions? They are gas ions, and gas ions they follow the Boltzmann distribution of velocities. So the Boltzmann distribution of velocities was extended to charge to determine a distribution, and they hypothesized they said that there is an equilibrium condition which will reach after a while. So if whatever be the initial concentration or the distribution of the aerosol, if you put it in a bipolar distribution, after many collision, they will also reach to a new equilibrium, which can be described by this Boltzmann charge distribution. They assume there is a uniform distribution. What do you mean by uniform distribution? That equal number of positive and negative charges are there. So this bipolar charging, diffusion charging, is also sometimes referred to as neutralization. Okay, so this is one theory, but it was observed that it is not the case, that the distribution is not uniform all the time. So for that, another theory was used, given by Fuchs and then approximated by Weidensohler. So what was observed, that this singly charged particle, the aerosol particle with having the single charge fraction, they were higher as compared to the Boltzmann distribution. Okay, and also the negative fraction was higher compared to the positive one. So it means that they are not symmetrical, they are asymmetrical, as unlike the Boltzmann distribution. So for that, this is one theory. So it's not like this is the only theory. There are so many there are different models available, but we will we will just discuss this one. So okay, so this is the equation which can be used to find the distribution. So in this there is a approximation coefficient AI, which is given in this table, and these two graphs again this lower right side. So one is for the 50 nanometer. So if you do the calculation for this, and when you plot, you will see the distribution will look like this. So like if your 50 nanometer particles are there and they are having bipolar distribution, so the distribution will be this. So you will be knowing the distribution from this equation. So if you see this graph, the negative side particles are having little higher fraction compared to the positive charge. Similarly for the 500 nanometer. Okay. So now moving to the second another charging mechanism. So this completes your R diffusion charging bipolar distribution. So then one instrument which most of us must have used is the nebulizer or the atomizer. So what happens in atomizer? In atomizer, we disrupt the liquid surface. We have something in our bottle, the liquid, the salt solution, maybe NaCl or whatever salt you want to generate, and you nebulize. You nebulize means you disrupt that surface and you break the liquid particles into the smaller aerosols. Okay, so what is happening? It is the static electrification, the one of the mechanism which we saw in the previous slide, and the sub part was spray electrification or the spray charging. So if we have in most of the cases, we are basically dissolving any salt in water. And what is water? Water is H2O. H2O is having this type of structure. So the lone pair, the dot which you are seeing, they are the oxygen molecule with the lone pair. So the oxygen molecule is bulky with the lone pair. So the arrangement of the H2O molecule will be such that the lone pair will be towards the outer side to minimize the tension. So the second figure is showing roughly how that will look like. So there will be an outer layer with the partial negative charge, the inner layer partial positive charge. So we can call it electrical double layer. Okay. So when you're disrupting this electrical double layer, the charging will occur. So your atomized aerosol particle will have charge. And then, but you are not going to use pure water, correct? You are going to dissolve something in it. So what will happen when you will add, for example, NaCl, KCl, any solution to it? It will disrupt this double layer. So it was found that the addition of any ionic compound reduces the charge. How it is thus? Because it will disrupt and some of the charges may be neutralized. The dielectric coefficient, the dielectric constant will decrease. So for this theory was given by Smoluchny. So again, we can just see the relation that how it is dependent on the the parameters. So you can see the dependence on dielectric constant. So more the dielectric constant, more will be the charge, and dielectric constant is having the inverse relation with the ion constant. So for example, you have three solution: 1% NaCl solution, 5% NaCl solution, 10% NaCl solution. What will be the charge carried by those particles? It will be maximum for 1%. As you increase more and more salt, the charge on the particle will decrease. Okay. Then second, one more generator we will see. So we can also generate the particles by electrically heating a metal or the wire. So suppose we have a wire of any metal, gold or maybe some alloy like nichrome. So when we electrically heat a wire, what happens? The vapors are emitted, and those vapors they nucleate and coagulate to form aerosol particle. So it is gas to particle conversion. So in that process also the charge will be generated. So now we will see how the charge is generated in that processes when you electrically heat a wire. So in that process, there are two mechanisms by which the charge particle can generate. So this is very like a useful instrument to generate a nano size. So this is one of the nano size generators. So if you want to generate the nanoparticles, we use this methodology, this generator for the aerosol generation. So what happens? Suppose, for example, you are having an alloy nichrome, where there are two metals. So one of them will definitely have a high evaporation rate, and it might coincidentally have a low ionization. So such an example is nichrome. So nichrome is having a base of nickel with the absorbent as chromium. So chromium has low ionization energy compared to the nickel, and it has high evaporation rate. So when you will start heating, what will happen? The chromium can transfer its electron from chromium to nickel. So it is what it is leading to? It is leading to the ionization of chromium. But since they are having, they are in the proximity, the energy requirement is less. So it will lead to the formation of the positive ion. And this process is known as surface ionization. Second thing which can happen is the thermionic emission. This is well known. What happens when you electrically heat a wire? At the point where you provide the sufficient energy to electron equivalent to the work function, it will lead to the emission of that electron, and that is the discharge leading to thermionic emission. But the energy requirement for the thermionic emission is very high. But because of the surface ionization, if there is an impurity, or there you have an alloy, you can create charge at the lower energy requirement. So these are the equations. We will not go into the details, but using these equations, the evaporation rate, the positive flux density, negative flux density, current density can be calculated. So I have done this calculation. So if you see for nichrome, so if you see this bar, they are the positive and negative charges. So the dark brown, they are the positive flux, and the light this pink, they are the negative. So if you see till roughly 2200 Kelvin, the positive emission is dominating. So till the time you give 2200 Kelvin temperature to that wire, you will not be providing sufficient energy for thermionic emission, and your process or the charges on the particles will be of positive polarity. So but when you go beyond 2400, your thermionic emission will be leading. But when you heat, usually we do not go to that high temperature. We are roughly around like 1800, 2000, obviously depending on your requirement. But at the lower temperature, you are having the positive charge. So when you will measure for this, so it is like counterintuitive, because thermionic emission is known to everybody that electrical heating should give negative ions, negative electrons. But when you will measure, you will get the positive charge because of that. So now this completes the few of the important charging mechanism or the processes which we use in our lab and their corresponding charging mechanism. Now we will move to the instrumentation, which utilize these electrical properties. Okay. So we will discuss these three important instruments. One is scanning mobility particle sizer. I think well known to everybody, discussed yesterday also. We will see little more details about that. Then we will see the aerosol electrometer. This is an instrument which gives you total aerosol current, and also the number concentration can be determined. And also this is used as a calibration for CPC, condensation particle counter. Then we have one more instrument, electrical low pressure impactor. This instrument is cascade impactor based, but utilizing the electrical properties. This instrument has modified the impactor to give you the number size distribution. Normally in impactor, what we get? We get the mass size distribution or maybe activity charge distribution. But using this technique, your impactor will give you number size distribution. And also you can find the charge. So we will see these three in details. So these points, the basic was discussed yesterday, but I will just revise. So there are four main components of SMPS. One is pre-impactor, which will act as a cutoff for the largest size, because we are going to limit our size range, may for example, like 10 nanometer to 1000 nanometer. So there is no point in, contaminating your impactor. So there is a cutoff for the largest size. Then we have bipolar diffusion charger, because we need to know the charge. So for that, we will impart a charge. And so for that, we are having a charger, which can be X-ray, which can be like mostly it is a radioactive source, which will give you the bipolar ion environment. Then we have a differential mobility analyzer, DMA, which classify your particle based on the electrical mobility. And finally, you have to count that. So for that, condensation particle counter is there. So CPC was discussed in detail. So I will skip the CPC part. We will focus on second and third. So so it is like till now it is clear that from this system we are getting what we are getting. We are getting the electrical size distribution. Okay, so we have to convert that electrical charge size distribution to your number size distribution, because you do not want the electrical distribution, no, you want the number distribution. So for that there is a inversion routine. So which basically for that we need to know three things. So one is obviously the thing which you want to convert, that is your electrical mobility distribution. Then we need to know the bipolar charge distribution. And then finally, there is one more thing, transfer function. So we will see little bit about these things. So starting with DMA. So what a DMA does? In DMA, you have different size particle, okay, which you are inserting in your annular ring. And there are two types of flow. So if you see this first, so if you see this thing, they are annular rods. Inside we have a sheet flow. What is sheet flow? That is filtered air, which is providing the laminarity, so that your particles which are going to transverse at the outer layer, they do not go to the central rod, because you're applying voltage at the central rod. So you want your particle from the inlet. So that is the inlet. If you can see that aerosol in, from there you want your particle to go to the rod. And so from your aerosol in, you want the particles to go to the central rod only because of the electrical or the charge they carry, not because of the diffusion, not because of just gravity or anything else. So for that you have to provide a sheet or a partition. So that partition is your laminar flow or the sheet flow. And then you want you want your particles to segregate based on the electrical mobility. So as we saw that electrical mobility depends on two things, the charge they carry and the size. So you have fixed the charge because you have put the bipolar charger. So your charge is fixed. You know the charge. And how do you know the charge? That also we saw that, like for the example, there is a Fuchs theory. So you from the Fuchs theory or the Weiden-Solar approximation, you know the charge. So charge is known. Only unknown is your diameter. So your particle of different sizes. So if it is your this is your inlet and you have three mobilities. So and you are applying the voltage. Okay. So for example, at the X voltage, there will be only one mobility class which will travel this path. The other will they will terminate at the top, or they will go beyond. And then one by one, you will scan the voltage. Hence the name is scanning mobility. So you are scanning the mobility. So your voltage is changing, and as your voltage is changing, the mobility class which will exit this slit is also changing. So there are at different time, different particles will exit this slit. So this is the equation. So this equation is known. This is the mobility equation. And then this there was the formula. One more formula was given by Zhao, and he related with the sheet flow also. So this is the diameter of radius of the inner rod and the outer rod. This is the length. This is the voltage. This is the flow rate. So from this equation, you can know the particle size. If your voltage is fixed, how your voltage is fixed, because you are giving the voltages. So from this equation, you can at least find the corresponding to what voltage, what mobility size classes are exiting this slit. Okay. So now next question is, now we are having the mobility classes. So if you see this graph, this is your size 1 with +1 charge, size 2, which is of with less concentration of +2, +3. But these 3 diameter, they all are having the same mobility. Why? Because as you increase the diameter, you supplied the more charge, and it depends on the charge and diameter. So if you are increasing the diameter at the same time you increase the charge, so they will correspond to the same wind. Okay, so we want something like this, but we are getting this. So for when we are saying that this one particle is coming here, so it is not basically one particle. 3 particles, for example, they are coming having 3 different charges and 3 different size. But we want to know this thing. So that can be done. That is known as the multiple charge correction, and that can be very easily done if you know the initial charge distribution, like what mobility classes correspond to these fraction. So you can, from the approximation, you can calculate the corresponding to diameter. At this mobility diameter, what composition or the what combination will give you this mobility, and then you can club it or the subtract from the later stages and add on. Okay. So then the third thing, we are expecting a single mobility class to exit from the slit, but that is not the case. Always there is a range. But when you are putting in, you want to determine the actual thing, you need to know the calculation or the model for the same. So the particle which exit, they are in the triangular transfer function. So basically the particle which are coming out of here, the mobility size mobility, they will have this type of distribution. Now the single mobility class is coming. So first of all, a distribution or range of mobilities of particles are coming, and then those mobilities also, they are having different peaks, like multiple. So you need to know the transfer function to correct for this, and also you need to know the multiple charge correction to get the accurate number size distribution. And then this broadening, it depends on the operating condition. What are the flow rates? There can be diffusion losses if the geometry is improper. Diffusion broadening is there. So so these are the equations for this. So this is not very simple. I have just given the introduction for this. So there is a detailed modeling to arrive at the transfer function. So we can discuss a little bit more in the afternoon session about this transfer function. So this is just small animation for the SMPS operation, DMA. So you can see the only a single charge particle. After when you charge, it goes inside this slit, and this slit is attached to your counter, and rest of the particles, they are going out. And here is a charger which is imparting the known bipolar distribution. So this SMPS can be, so we saw that there is a sheet flow, right? And the flow rate, the ratios between, in general, the ratio between the sheet flow and the aerosol flow is 1:10. So that means the volume of the sheet is roughly 10 times more than the aerosol. So the humidity of the sheet flow, that also influences the distribution. So if you see this, this is the graph for NaCl. So this black line, it is when you have dried the sheet air. So you are having a sheet air path. If you see this SMPS, which we will show, this is sheet air path. So if you do not do any, you can modify the sheet air path using a dryer. So if you modify the sheet air path using the dryer, your distribution is something else. And when your sheet air is having the 90% humidity, for example, your distribution is like this. So it means that you cannot use your SMPS at any humidity. Depending on your requirement, if you are interested in the dry size or you are interested in the particle size at, for example, 60% humidity, you need to maintain your sheet air humidity at that level. So moving on to the second instrument, aerosol electrometer. So it is basically based on the Faraday cup principle. You are having a metal cage or cup type of a structure where your aerosol particles are coming, and that cup is attached to the electrometer. So whatever the charge is being induced by the incoming particles, that is being recorded, that is being imparted to that metallic cup, and the change in the current will be ultimately reflected in the electrometer. So using this type of this electrometer, you can get the total charge carried by the particle. You cannot not segregate because it is just a cup. So whatever all the particles, whatever is whatever are coming inside that cup, they will be counted for their charge. Then using that, since charge or the current is the basic unit, basic property. So using this electrometer, the CPCs are being calibrated. So for that, this equation is there, which relates your number concentration with the current. But again, when you are relating, you need to know the charge, because again, you directly you cannot relate. So if you want to calibrate, you need to know the charge on the particles from which you are calibrating. So the known charge particles, they are measured from the CPC as well as the electrometer. So this is the CPC concentration. This is the electrometer concentration. Okay. So for calibration, one thing is you need monodisperse aerosols, and then you need, the known charge. That is very important. And from this equation, you can convert the current measured by the electrometer to the number, and then you can compare this number with the CPC. Coming to third and the final instrument, the electrical low pressure impactor. As the name suggests, we have an impactor, we have low pressure, and we have electrical connection, electrical something. Okay, so so what it is, as I told, that this is a this gives you number size distribution and charge size distribution, and the size ranges from 6 nanometer to 10 micrometer. So 6 nanometer is very small for an impactor. So basically, this is a very sophisticated, finely designed impact the design. So in this, we have a three major part. One is charging. So whenever we are having number distribution, so somewhere you need to, and using the electrical properties, you need to know the charge. Then only you can somehow relate the current to the number. So you have a charging mechanism, then you have a cascade impactor, you have an electrical detection. So this is the basic schematic. These are the impactor plates. You have a charger. This we will show you in the second half session. And then the electrometer arrangement. So to each impactor stages, so there are 14 impactor stages. To each impactor stages, electrometer needle is attached. So whatever change is there, that is being recorded by the electrometer. So what is happening? You have a charger. The particles are charged. They are going one by one in the cascade impactor. And depending on their size, inertia, they will be segregated in the impactor. And since to each impactor, the electrometers are attached. So what will happen? The change in the plate. So again, this is like a Faraday cup only. You have an impactor, metallic impactor. So you can see here. So these are the impactors. So you have a paraticular type of structure. So whatever particles are collecting, they will change the current, and the change in the current will be measured by the electrometer. And this will happen for each size. Okay. So and then since charger is there at the top, you can relate that charge with the numbers. But since that the charger is there and you're segregating, there is one option that you can keep the charger off. So what will happen if you keep the charger off? It will measure something. You will get the charge size distribution because you have turned off the charger. When charger is off, you cannot get the number information, because for number information you need to know one parameter to relate to the other. But electrometer will measure somehow something. The current it is measuring. So what is that current? It is measuring the actual current. So the actual current or the actual charge carried by the aerosol particles that are depositing on the impactor will be measured by the electrometer. Clear? So that is why it can be used as both the number size distribution and the charge size distribution. So when you keep the charger off, it will give you the actual charge carried by the aerosol particle. And that information will be size-wise. Why size-wise? Because you are segregating in the impactor. So each impactor is having a size information. You are measuring current also. So you will get the number size, charge size distribution. And when you turn the charger on, you are converting basically, you are basically destroying the original information. So the original charge carried by it will be eliminated. It will now carry the charge which you have imparted using your charger. And that known charge will be converted to numbers. So now we have different types of plates. Again, that we will show. So the impactor plates, we have basically two types of impactor plates. One is the alumina base. If you would have seen the Modi impactor, there was the alumina foil, right? So those type of alumina foil can also use in this. And then there is one sintered plate. So one experiment was done. So in this, this group saw that with time, if you do experiment with the sintered plate, the grease, aluminium, all those things. So what will happen for the sintered? If you see the geometric mean and the number distribution, they are parallel. They are not changing. They are constant. Whereas in the other cases, they are decreasing or increasing. Why? Because the alumina plates or the normal alumina substrate, they will get saturated very easily. And once they are saturated, the bouncing effect will come. In impactor, if you remember, why the shape is not like S, why it is curved. Remember? It is because of the bouncing effect. The lower size particle, the upper size particle will bounce out to the other stages. So, but the sintered plates, if you see here, so these are the normal plates and these are the sintered plates. So because of its design, they hold all the particles nicely compared to the normal alumina plate. So it's better. So it's important to know what substrate you are using. Like even on the impactor, if you are using filter papers, alumina, you should know that after what it will become saturated, and because of bounce of effect, your results will become inaccurate. So if you see the number concentration, the huge difference. If we assume these are the correct, so all other plates are underreporting. So that will happen with any impactor. It's not specific to ELPI. This is for any impactor. So this is important to know till what time that bouncing effect will come. So charger, this we have discussed many times. So the charger is corona base. Okay, the corona base, and the charge the ions are generated, and these ions impart the known charge to the upcoming or the incoming aerosols, and the charge or the ion flow is controlled by the current. So we give some current and the voltage. The voltage is to generate the corona, and the current is to maintain that flow to give the known charge. Then the most important thing, like how you are converting the charge into current number. So for that, this is the basic equation that you can relate the current, the concentration to current. This you are measuring, this you are measuring. But there is one, this P and EQ, which is not known. You need to know. So in many cases, we had some theoretical basis, but for ELPI, the basis is empirical relation. So experiments were carried out multiple times, and from the experimentation, empirical relation is determined, which is this. So for this value is for DP less than 1.035 micron. The value is different for this range, and for greater than 4 micron, the value is this. So from this charger efficiency function and this relation, you can convert, or your software automatically converts your current into the charge number. Clear? So that's how you get the number size distribution from ELPI and charge size distribution from the ELPI. So while doing the study from this instrument, what we observe that the value of the charge given by the software is wrong, or is it's giving higher value what it should actually give. So what was happening? So as I told that there is two mode, charger and on and charger and charger off. So by toggling it, like charger on for example 20 seconds, charger off for 20 seconds, we will get the both information, number as well as size. And when you divide, what you will get? Charge per particle. Okay. So the charge per particle, this is the Excel sheet. Again, we will show this to you. So if you see the Excel sheet, so these are the charger on values and these are the charger off values. So if you see this, for example, this channel 6, what is the charge current? The current is roughly 28,000. Okay. And then next moment, what did you did? You turned off the charger. So what it should do? It should tell the actual value, actual charge carried by the particle. But what was happening that it was carrying this information, the earlier information. So if you see it was 28,000, the first reading is again 27,000, same. And it took few seconds. And that time is also different. Like for few species, after 2 or 3 seconds, it will go to the original charge. And for some species, it took 4 to 5 seconds also. So after 3 seconds, it came to the actual value. So what will happen if you take average of this and average of this, because you are interested in charge per particle. So this, even though the value, one value is there or two in some cases, but the value is so large compared to the actual charge. The actual charge is, for example, 800 current femtoampere. Actual current is 800 femtoampere, and it is in the charger on condition, it was 27,000. So when you will average, simple mathematically, that one value of 27,000 will distort your result. Correct now? So because of this error, or maybe this error, the software was giving the high values. And when we did the calculation, removing these values, and we studied this for different species. For some species like sodium carbonate, this was changing the polarity, that this effect was so prominent that you got the different polarity in the software, from the software and from the manual calculation. Okay, so this is for the NaCl. If you see, the manual calculated values are less and for the software calculated values are more. So for that, we develop a Python program to do this calculation rather than using the software. So again, it is important to know what your software is giving. You cannot use it as a black box, because whatever you will report directly from, because most of the people will report this and paper will also get published, but those values are not correct. So, okay, so you need to understand these things also, and you see how your software is giving you what it is giving. Then we did few more actual experiments with the ELPI. So these species, NaCl, sodium nitrate, carbonate, etc. With the ELPI, and we measure the charge per particle. So what we observe that this charge carried by this particle is dependent on the species also. Like you can, if you see the sodium carbonate and NaCl, this size 0.04 micron, one is giving you positive polarity, the other is giving you negative polarity. So you cannot take one value and do all your calculation. When you extend this to the deposition theory, when you will see there, the deposition is in some cases as high as 7. So if you wouldn't have done the experiment for a particular species of a particular chemical, you would have got wrong results in your calculations when you may be determining the deposition fraction in the lungs, in the pipes, or for any equation where you just take a average value or the random value for the charge. So this study highlights that it is important to take the actual measurement rather than and that which is dependent on a species also. No, even though it is dependent on charge, obviously it is different for different size. But this is it's a little known that the charge depends on the size of the particle. But it is just one of the parameter, the size. The other parameter is also species. So for charge measurement, you need the proper experiments. For whatever, even if you are going to do the theoretical studies, the input should be properly experimentally determined. Okay. Yeah. Thank you. Questions? Thank you. Okay, yes, sorry.
So regarding this ELPI, so you told that if the actual like aerosol charge distribution will be turning off your neutralizer or charger.
Yeah.
Right. So like if you are with neutralizer and without neutralizer, what are the wall losses? So whether is there any behavior of your
actually, one study is there on that thing. I think by Chen et al. In 2014, they did that thing. That whether when they are turning off the charger and when they are manually removing it and doing the experiment.
Because the Brownian motion will change.
Yeah, they did that study in 2014. I think 14 or 15. They did that study. They turned it off and then they removed it. That charger assembly, if you see in the instrument, it is removable. They removed it and that they didn't observe much difference.
So that loss is negligible.
Yeah, it's negligible. Yes.
And so what is the flow of this ELPI?
10 LPM.
10.
Yeah, large.
So you so and the flow is 10 LPM. What is the size of the lane from the charger to your ELPI? So
it must be roughly 10 centimeter, 9-10 centimeter.
if it's 10 LPM, like it should not take much, like even 1 second also to break or remove all the charges. Right?
From where?
Because your volume is being sucked out, right?
Yeah.
So the LPM, the 10 LPM.
It is going toward the impactor. It's kind of impactor assembly, and above that the charger is there.
Yes, but you're sucking with the 10 LPM volume.
Yeah.
So the residue of the earlier charges, right? Because you're
but that is the case now. They also assume that thing. So that's why they must have not thought of doing this thing or putting some toggling factor or the transition time. But that is what is happening. And we did the experiment for many species. So for some it is taking 2 seconds, but for some it was taking 4 to 5 seconds also. So 2-3 readings with that huge number like 10⁴ will contribute or change your number drastically.
like expenses of your charge.
Yeah, somehow it is.
Exponential goes down.
Yeah, it takes some time. Yeah.
Thank you.
Yeah, thank you.
Okay, thank you. Thank you, Mariam, for the informative talk. Now we will invite Mr. Subrata Mukherjee from IITM to deliver his lecture. Mr. Subrata Mukherjee works on aerosol physical and chemical characterization, VOCs, and aerosol CCN activation. Welcome, Subrata.
Hi. Good morning, all. So, my talk will be mostly on aerosol hygroscopic growth and its impact on aerosol to cesium activation. Okay. So, Mariam has rightly set the stage for me because she has covered most of the part theoretically, but I'll be missing out. Okay. So mostly on SMPS. Uh, my talk will be mostly interactive. So I'll be asking some of the questions to you also. You have to respond so that I should be able to know that you are getting something. Okay. So my outline of the talk will be mostly I'll be trying to define hygroscopicity. Then I'll try to describe why hygroscopicity is important, whether it is really important or not, and what is the basis of using hygroscopicity or sizes for aerosol to CCN activation studies. And I try to elaborate more on different ways to measure hygroscopicity. So based on direct measurements through different instrumentations, or with the indirect ones if we don't have the direct instrumentations. Then I'll try to show some of the results from our lab, so which we have already published or we are doing already. Okay, so basically, hygroscopicity is basically the ability of water uptake by aerosols that are present in the atmosphere. Okay, so absorption and release of hygroscopicities that depends on the nature of the aerosol particles. So how much hygroscopic those aerosol particles are. And if we want to express that hygroscopicity or hygroscopic growth factor, so that is defined as a ratio of your dry diameter, that is basically particle diameter, which is being dried, okay, with using diffusion dryer or Nepean dryer, and with a wet diameter. Wet diameter is basically when you are exposing a aerosol particle into a humidified environment, with a definite humidity 40% or 50% or 60%. So what is the growth of that dry diameter into a larger one? So that wet diameter, the ratio of that wet diameter to dry diameter will give you the growth factor. Okay. So in that way, we can express this hygroscopic growth factor. So there is a small question I have posed into. So if you keep your salt or sugar jars during monsoon season open, so what will happen? What you tend to see? So it will be moist and it will absorb water. So that tells you about the role of hygroscopicity in terms of aerosols. Because salts, we basically use it as aerosols, they're present as aerosols as well. But the sugar is basically an organic compound. So it's not only the inorganic ones that tends to absorb water, it's the organic ones as well. So both are playing a major role in atmosphere for absorbing water and ultimate growth towards cloud droplets. Okay. So I think this kind of graph you have already seen. I will not be explaining much. So there are different ways of emissions of aerosols into the atmosphere. First one is the sea spray, that is a natural source. So there can be a dust incursion also through wind driven dust incursion. So there might be this thermal power plant or industrial sources as well that can also inject aerosols into the atmosphere. And there are biogenic emissions also, not directly to aerosols, but through volatile organic compounds that can get converted into aerosols. Okay. So once these aerosols are emitted into the atmosphere, they generally undergoes into different kind of photochemical oxidations, both the inorganics and organics ones. So if you see in terms of gaseous, so inorganics are basically sulfate, nitrate, ammonia. So they are being exposed to the photochemical aging, and after that, so it will tend to form a low volatile substances which will tend to go into the particle phase and form aerosols. So they can either deposit onto existing particle surface, like if you have dust or sea salt into your atmosphere, so they will get a surface and they will tend to deposit because of the low vapor pressure, or they tend to form aerosol particles as well. That we term it as nucleation. Okay. So there is an interesting thing is that when you expose these aerosols into different RH environments, so they undergoes different kind of processes. One of the process is diluent process. So diluent process is basically when your aerosol particle is completely dissolved into your aqueous phase. And the efflorescence process is the just opposite to that. Okay. So when suppose you are forming a cloud, so you are doing diluents of your aerosols into the moisture laden aerosol particles.
When you are doing efflorescence, it's basically your cloud is dying out and your whatever aerosol residues are there that are being left into the atmosphere. So there is a change in your phase as well as change in your chemical properties due to this heterogeneous like phase transfer as well as chemical transfer processes. Okay, so that will change your chemical property as well as your hygroscopic property as well. So like when we define this role of hygroscopicity or sizes on like aerosol to cloud activation, so the most prominent theory that we like refer to is the Koehler theory. Okay, so Koehler theory, like Koehler has already developed this theory way back in 1936. So he has like combined the effect of curvature, that we term it as Kelvin effect, and the effect of this solute, that the composition, that is a Raoult effect. Okay, so when you want to see the effect of Kelvin effect, it's basically depends on the size of the aerosol. Suppose I have now you try to consider a bigger particle and a few number of smaller particles. Consider this as this has the same volume as this many number of particles. Okay, so now try to see, can you please tell like which this set of particles or the bigger one has the highest surface area? The smaller ones, right? Okay, so the Kelvin effect, what it basically gives. So do you know about this vapor pressure? You know, right? So it's a pressure that is being exerted onto your aqueous or any liquid surfaces, okay, by the vapor, corresponding vapor. Okay, so like when you have higher surface area, so if you want to maintain a vapor pressure in equilibrium, thermodynamic equilibrium, you need more number of water vapors around your particle surfaces. Okay, if you have a bigger one, you need lesser water molecules. If you have smaller sizes of n number of particles, you will need larger water molecules. Okay, larger number of water molecules. So higher number of water molecules, what does it mean? It means basically you have to increase your humidity level to a certain extent that it should establish some kind of equilibrium. Okay, so from that thing, you can infer that for a larger particle, if it is there in the atmosphere, you need lesser humidity, or I can say lesser supersaturation. Supersaturation is nothing but more than 100% humidity. So how much we are getting? Okay, so you need lesser supersaturation or lesser water content in your atmosphere for larger particles, and higher water content you need for smaller particles. Okay, so that's why. So when you try to see this graph, so this is basically a Kelvin curve. Okay, so it is going towards infinity when you don't have any particles into it. So suppose it's a pure water droplet or pure water, okay, molecules. So in order to make that into a particle and to grow, you need infinite relative humidity conditions or supersaturation conditions. Okay, so when you increase the size of your seed particles, so the effect will tend to decrease. Okay, and the Raoult effect, that is basically a solute effect. So that tends to work in the other way. If you have hygroscopic particles, it will tend to accept your moistures. Okay, so the combined effect of both both this Kelvin and Raoult's term will give you a combined curve. So it looks like, if you can guess, it looks like a activation or energy curve. So the particle needs this much of energy to get activated into cloud droplet. Okay, so this maximum point can be considered for that diameter as a critical supersaturation. So that critical supersaturation is the minimum supersaturation that is needed for the particle to grow. Okay, other else it will evaporate and grow. like it will be like equilibrium. So it won't grow further. Okay. So this Kelvin, like this Kohler theory, like or Kohler equation can be expressed in this term. So where you can see this sigma is basically the surface tension of your water. MW is the molecular weight of water. Sigma is the density. RNT you know. So the droplet is the droplet diameter. Okay. So you have your curvature term here. So this term is called as the curvature term or the Kelvin term. It depends on the size. You have one water activity term, which can be referred to your aerosol hygroscopicity. So there are enormous number of parameterizations, but the most widely used parameterization is based on the Peters and Kendrick 2009. They have published one paper on that. So they have expressed this water activity as the like in relation with the kappa and the particle dry diameter and the droplet diameter. Okay. So now these things are clear, right? So here actually I am trying to give some examples based on the solute effect and the curvature effect. So if you see closely here, so if you are increasing your concentrations, so these are basically your NaCl or sodium chloride solutions that you are nebulizing it and doing all the calculations. Okay, so this will be in the particle phase, not in the liquid phase. So if you are having this amount of NaCl like 10 to the minus 19, this is the least one. So you see the activation curve, that is the second one. Okay, so this one. So this is way higher than that of your 3 and 4. So that means if you increase your mass of your seed particles, so your activation curves is bound to go down. You will need lesser supersaturation to make the particle activated and act as cloud droplets. Okay. So if you see for two different molecules, now you try to compare this second and 5 or 6. Like second will be equivalent to 6. So you have in second 10 to the minus 19 kg of sodium chloride, and you have the same amount of ammonium sulfate. So you try to compare 2 and 5. So you see for ammonium sulfate, you need more supersaturation to get activated, and for sodium chloride, you need less. So that tells you about like the extent of hygroscopicity for a given particle, be it inorganic or organic, can influence your extent of growth as well. You need more supersaturation for certain particles. You need less supersaturation for certain particles as well. Similarly, if you try to see in terms of Kelvin effect, suppose if you compare like 50 nanometer, this is basically 0.05 micrometer, that means 50 nanometer. So here we have 100 nanometer and where we have 500 nanometer. So if you see here, the supersaturation that it takes to make the particle activated, it's very high for lower sizes. When you increase the size, so the like supersaturation needed for activation, it goes very low. So by the time it reaches 500 nanometer in a real atmosphere, the required RH is almost 100%. So if you have 100% RH in your atmosphere, so 500 nanometer particle can easily get activated. Okay, and this is for the inorganic ammonium sulfate. Okay. Okay, so now I'll try to explain whether this aerosol hygroscopicity is really important. So we have seen some of the indications that aerosol hygroscopicity can play a major role, but whether it's really important in comparison to size, because there are two contrasting effects, like one is the size, one is the hygroscopicity. So there was a nice paper by Dusek et al. In 2006. I don't know like how many of you have read that. So they tried to see whether size or the chemical compositions or hygroscopicity matters more in terms of aerosol to CCN activation. So what they tried to do, so this is actually the model CCN. That means it is calculated based on the Kohler theory that we are like seeing now. And this is the actual observation from the CCN counter that I'll be explaining afterwards. Okay. So you try to see that when they have made the composition constant. So how they have made the composition constant? So you have aerosol size distribution. So you consider a average activation fraction for each sizes. So that makes your composition constant. It's an indirect way, not the direct way, but it's an indirect way to make your composition constant. And you take all the real-time size distribution to calculate your model CCN. So, and in this way, and in the second scenario, So what you are doing, you are making a size distribution constant, and you are varying your activation fractions for different sizes. Okay. So while comparing with both the cases, you could see that when we are making composition constant, so the comparison of model CCN to measured CCN is clearly 1:1 line, and it is following. But if you do the other way around, making size distribution constant and keeping your activation fraction changed, so you are not getting any relation, good relations. It's not even on the 1:1 line. So what does it tell? It tells that size is basically more important as compared to the chemical compositions. But it's not the single study. There are other study contrasting to this results as well, because science is not like a rigid thing, so it will evolve. Okay. So there is a paper, a nice paper with Kawana et al. In 2016. So what they have tried to do actually, so this G is basically growth factor that we have studied. It's a ratio of wet diameter to dry diameter. It's nothing else. Okay. So what they have tried to do actually, they have incorporated size and time resolved G, and in one cases they have considered only single average value of G. Okay. So what they have found actually comparing with the same, this is basically NCCN to CN. That means it's basically CCN only, but in an activation form. Like they are dividing it with the total number concentrations. Okay. So what they have tried to see actually, so they have tried to see that whether this single G is enough to explain everything, or you need a more higher resolution and higher size and time resolution of G, variation of G. G is basically indirect measure of your aerosol hygroscopicity. So what they have found that if you give more accurate information of growth factor or hygroscopicity, so your relationship with the model predicted ones versus the observed ones, it will tend to improve. Okay, so it doesn't mean that only size matters, size of the aerosol particle matters. In addition to size of the aerosol particles, your hygroscopicity or the growth factors also matters in the equal way. Okay. So there are different ways to measure this aerosol hygroscopicity. One is the direct measurement of hygroscopicity. Okay, that we for that we utilize humidifier tandem differential mobility analyzer. So there are other indirect ways to estimate your hygroscopicity as well. Like if you don't have this instrument setup, you can utilize your passive informations to derive or estimate some kind of hygroscopicity, which you can utilize for your CCN prediction or cloud CCN to cloud activation, aerosol to cloud activation. So this indirect estimation of hygroscopicity involves the informations of chemical composition from either aerosol mass spectrometer or SCSM, or any even if you get the inorganic informations also, that will also do a fair enough job. Okay, and you can also derive the hygroscopicity if you have only this SMPS that Mariam covered, and the CCN measurement also. So you can directly calculate that as well. So I'll try to explain all those aspects. So this humidifier tandem differential mobility analyzer we basically use to directly measure hygroscopicity, aerosol hygroscopicity. Okay, so it's a combination of two SMPS basically. One we run as a dry DMA, dry SEMS. One is a combination of a humidifier and a wet SEMS, that is humidified SEMS. Okay. So this is basically the diffusion dryer, which we always it's always advisable for your aerosol research. Whenever you are doing any measurements, you have to dry your aerosol particles, okay, to a certain level, preferably below 20%, or if not, if it should be below 40%, so that there is no growth in the aerosol particles. Okay. So this is the first DMA that we use as a dry DMA, where we try to select different aerosol particles. Okay, so it can range from 32 nanometer to up to 200 nanometer. Okay, and then we have a flow splitter. So where we we calculate whatever size we are choosing. Suppose it's so how many particles are there in the atmosphere in the size of 50 nanometer. Then and the other part we are sending it to humidifier, then followed by 8 SEMS. So I'll give the schematic of that also. Suppose you have polydispersed aerosol particles in your atmosphere, So you're feeding that polydispersed aerosol particles through a Nepean dryer to the initial DMA, and you're setting up the DMA sizes accordingly with a definite time intervals, like starting from 30 nanometer to up to 200 nanometer, depending on your applications, what you want to do. Okay. So now you have size selected it. It's now a monodispersed particles. Now these monodispersed particles are being subject to the humidifier, and this humidified air is coming from this Nepean water bath. If you can track this point A, so it's basically here. So from this point A, humidified air is being mixed with your sample air. That is the monodispersed aerosols. Okay. So this humidified air will transfer like water vapors to your sample air streamline, and it will help that particle to grow. Okay. And this like humidified water bath can be like controlled. So the RH we can control from starting from 20% to up to 93 to 98%, depending on the which type of humidifier you're using. Okay. So we have that flexibility. So we can study how it is growing at different RH exposure. Okay. So once it is grown, then we are sending that particle to a second DMA. So here actually we are maintaining the same RH of the initial like humidified ones. So there we are scanning a like complete size scan, complete voltage scan. So where we will be getting the size distribution. Okay. So this size distribution will tell us, so suppose for an initial size of 50 nanometer, how much it has grown. Because we need for growth factor calculation is basically the wet diameter and the dry diameter. Okay. So, and we'll be counting with these second MCPCs. So this is basically the like software interface that you will be seeing while your visit to like Mahabaleshwar tomorrow. I think people will show you this one. So I will be like spending much time on this. So see here actually whether you can see or not. So this is the set point of 20% humidity we have said for a dry size of 100 nanometer. Okay. So if you see the more diameter, so it's around exactly 100%. So what does it mean? It didn't grow anything at 20% of supersaturation. Okay. So when we expose the same aerosol particle at 90% supersaturation, okay, for the same size of 100 nanometer, it has grown up to 178 nanometer diameter. So there is an increase of 78 nanometer. Okay. So what will be the growth factor? Can anybody tell? .78. It's basically 178 divided by 100 nanometer. So exactly we get the same growth factor as 1.78. Okay. So this is the way actually we directly calculate the growth factor, and the growth factor can be converted into hygroscopy. So it is not like that. So here you can see there is a nice single like a Gaussian distribution. So it's fairly simple particle, but you won't be like always be fortunate enough to get a single peak. So you may get double peak as well. Okay. So why is it so? Can anybody like guess or anything? So why you will get this kind of double peak or triple peak for a single size? Have any idea? No, actually, basically, so when you select the size, you are selecting just sizes, not the particles. So particles have their individual properties. So there might be a presence at the same size. There might be a presence of sea salt. There might be a presence of dust. There might be presence of soot particles. There might be a presence of organic aerosols as well. So there are n number of different chemical like characteristic particles that are present in the same size. So if you are fortunate enough, you will end up with a single growth factor. And if you are not fortunate enough, so you will always, like it's in real atmosphere, you will always get for a particular size, you will get a multiple growth mode factors. Okay. So this is one of the example of that. So it's a bimodal distribution. So you have to calculate your growth factor as a weighted average of all these peaks. Okay. So you understood why it comes as this, right? It's clear, right? So like now we know this G value, that is the growth factor by diameter by dry diameter. So we know from this Euler curve or Kohler equation, all these parameters. D dry we know already, we have what we have fixed. We know the RH we are setting. So we can easily calculate this kappa directly from these useful informations. So I mentioned about this like multiple growth factors. Okay, so what you have to do actually, you have to do a weighted average to get a average growth factor to be utilized here for mean kappa calculation. Okay. So actually I posed already that question, but I asked earlier. So there are some ways to calculate, calibrate this HTDMA instrument. So it's not basically calibration; it is just to see the validation of whether your two SMPS and your humidifier is working properly with a minimal error or uncertainty with it. So to do that, actually we can send like different, I have mentioned about like ammonium sulfate solution. So you can send sodium chloride or anything, any known any known hygroscopic particles. You can send it to the instrument through nebulizer or atomizer. You can nebulize it and dry it first. Then you can send it to the HTDMA instrument. Okay, and you can check the growth of these particles with the exposure of different kind of relative humidity. So in your y-axis, it's growth factor. In your x-axis is relative humidity. And you can theoretically calculate the same growth factor for the known particle based on your Kohler theory. Okay. So what you can see here basically, so it's mostly tends to follow the Kohler curve with a error of plus minus 3.5%. Okay. But if you see here for RH at around 75 to 80, so there is a delay in activation. Okay. So can you guess what is the reason for this delay? I've mentioned in very earlier slides. It's because of the diluence point. So like aerosol particle needs to be dissolved first in order to act as CCM. So this delay is because of the diluence points. But once that particle reaches to that diluence point, it tends to follow the same theoretical curve. Okay. And like there are other ways to calculate the calibrate the HTDMA, because it's a combination of different set of instruments. Like HTDMA is not a single instrument; it's a combination of like two DMAs, like two SMPS and one humidifier. So these DMAs can be individually calibrated as per the calibration per standards. Okay. So now I'll be discussing a little more about chemical composition derived hygroscopicity. So in order to measure chemical composition, we mostly utilize aerosol mass spectrometer or aerosol chemical speciation monitoring. You might have heard many times till now. First day, I think many people has mentioned about it. So what is that instrument? Actually, this is actually the picture of the instruments that are running in HSEPL. So that you will be seeing it tomorrow, and people will explain all the principles and everything all together. So what we exactly get from these kind of measurements. So we tend to get this sulfate, nitrate, ammonium chloride, and organics. Okay. And we get only non-refractory ones. So whenever you see any papers related to AMS or ACSM, you will see always one term, non-refractory. So what do you mean by this non-refractory? Non-refractory is basically, so whatever is vaporizable, aerosols tend to vaporize, okay, so at different temperatures. So suppose if you have ammonium nitrate in your aerosol, so it will tend to vaporize at even 40 degrees as well, okay. So the non-refractory particles, when we term it as, so when that particles are vaporizable below 600 degrees centigrade. So those we term it as non-refractory, and whatever is not vaporizable like sodium chloride or any sea salt dust aerosols, so that will be refractory aerosols. Okay, so we don't get any refractory aerosols from this instrument. Okay, so all will be like a non-refractory ones which are vaporizable below 600. So this this technique actually, this measurement technique utilizes electron impact ionization. So it's a hard ionization technique. So ionization actually is done by two ways. One is the hard ionization, one is soft ionization. So in hard ionization, so the fragmentation of aerosol particles will be random. Okay, so it will be kind of a random. So it can be ruptured in any way. Okay, and for soft ionization, so your aerosol particles or the molecules that are there in the aerosols, their identity will be kept in soft ionization. We call like that soft ionization as chemical ionization as well. Okay. So for for these AMS measurements, we mostly utilize electron impact ionization technique. So where like you get fragments of particles, not exactly particles, it's fragment of signals. Okay, and from there we have to derive the actual aerosol masses. And this instrument has a high time resolution of 30 seconds, and it provides both the mass, total mass, aerosol mass of sulfate, nitrate, ammonium chloride, and organics, as well as their mass size distribution as well. Okay, so the main difference of this AMS and ACSM is basically for AMS, you will get both mass and mass size distribution, total mass and mass size distribution. For ACSM, you will get only the bulk mass contribution or bulk chemical composition. So this is the actually systematic way of operation, like how it is working. You can see here actually for HR top AMS, HR is basically high resolution. So high resolution in terms of like mass that I'll be explaining later. So time of flight, it's basically, it's a technique to segregate all the peaks, and it's aerosol mass spectrometer. So what we basically do, we send ambient aerosols from this particle inlet. So there is one aerodynamic lens which focuses your randomly like sized particles into a single stream, air stream. Okay. So then you have a chopper, so that selectively passes your aerosol as a packet. Okay. So there is a reason why we use chopper, because actually, so this region is basically a p-top region. So it's basically to determine the size of aerosols. Okay. So this length, if you see, actually this length is always defined. Okay. And starting from here to here, the length we know. Okay. And the time of flight we can calculate for each particles. Okay. So and it will always be in the form of microsecond time of flight. Okay. So and this is true only for the sizes up to 1 micrometer. So this part will give you the size informations, and from here to up to detector. So the time it takes, it's basically nanoseconds. Okay. So this time period is basically microsecond. This is nanoseconds. So there is a like difference of 10 to the power 3. So what people generally assume for the calculation is, by the time this particle reaches here to here, it will be immediately detected, because the time difference is basically in the order of 10 to the power 3. So suppose if I am size selecting one particle, okay, so it's not basically size selecting, it's basically sending all the size particles to that, depending on their sizes and their relative velocity. So it will reach at this point at different time intervals. Okay, suppose for 50 nanometer particle, it will travel fast. For 100 nanometer particle, it will travel slow. Okay, so once it reaches to this point, so there is a capture vaporizer where we keep the temperature as around 600 degree. So it will immediately vaporizes. Okay, and we have a tungsten filament here, which is also heated, which emits electron. So these electrons, emitted electrons, will immediately ionizes all these gaseous molecules which are being evaporated from these aerosol particles. Then it will be immediately detected as a mass, as unit mass. Okay. So in this detection, there is also like two types of detection is there. One is quadruple type of detection, and second one is a time of flight detection that we are using here. So in quadruple detection, we select voltages, and those voltages are corresponding to the different masses. Okay. So in SMPS, Mariam already mentioned that. So you have to select some voltages in order to get different sizes. So that you will be seeing in demonstration of SMPS as well. Okay. So similar analogy is there as well, but not for the particles, but for the masses. Okay. Do you know the mass of carbon dioxide? It's 44. Okay. So whenever you get CO2 here in the form of CO2, so in your detector, it will be detected as M by Z 44. Okay. So this is basically from particle to molecular transformation through evaporation and ionization. Okay. So this is the technique for this AMS. It is very a complex instrument. Okay, but if you see for ACSM, what I mentioned actually, ACSM is mostly for the bulk chemical composition. It's a fairly simple one. Okay, so what we basically do, we tend to sample in the same way with aerodynamic lens. We pass it and detect through a more robust detector. Okay, so the catch is that, so whenever we are sending the particles, aerosols, so it will be like in a two mode. So one where we'll be sending all the aerosol particles with the air. And in another one, we'll be applying a filter where aerosol particles will be cut off. Okay, so there will be only gaseous that are available that will tend to pass from here. So the difference of this aerosol plus gas and the gas will give you aerosol chemical composition. Understood? So and the same analogy is here as well, but not in the form of filters, but in the form of this chopper position. So you can close it, you can open it, or you can run it in a pit-off mode. Okay, it's clear, right? So this is a kind of tentative mass spectrum of the aerosols that are being detected at Mahabaleshwar. So if you see here for sulfate, what is the molecular weight of sulfate? Can anybody tell? So I've written here as 96, but H2SO4, if you see, it's 98. Okay. So when these sulfate aerosols are being subject to the capture, vaporizer, then ionization and detection, so it will give a mass fraction peak at M by Z 98, 81, 80. 80 is for SO3 plus, then 64 is for SO2 plus, 48 is for SO plus, and this 32 is for S plus. Okay, so this many fragmentations will happen because of the hard impact ionization. If you see for nitrate, so it's the molecular weight is 62, but you will mostly get all the peaks at 46 and 30. Similarly, for ammonium, its molecular weight is 18, so you will get a major peak at 18, then 16, 17, and 16. Okay, so if you see here, actually for organics, the masses are spread widely, but for inorganics, it's fairly straightforward. Okay, so that's why whenever you tend to search more on these kind of aerosols, you will always see people will tell you organics are more complex as compared to inorganics, because for inorganics you can see there are defined peaks you can easily interpret or you can easily estimate, but for the organics it's spread widely. Okay, and you cannot infer anything from this. Okay, until unless you have prerequisite informations. Okay. So there are different ways to calculate, calibrate this AMS. So basically, AMS we are getting size and chemical composition. So we have to do size calibration as well and the chemical composition calibration as well. Okay. So for chemical composition, we mostly calculate ionization efficiency. So what we do basically, we use mostly for our most of the instruments. This is the most useful instrument tool that we use, that is nebulizer or atomizer. We have to atomize all the aerosols and feed into instruments. And mostly we use SMPS as well for size selecting and CPC for the counts. So all these things are needed for the calibration of most of the instruments, like state-of-the-art instruments. So we need that kind of instrumentations. So we try to pass mostly ammonium nitrate aerosol particles, because ammonium nitrate has the highest efficiency of vaporization and ionization. So for that purpose, we mostly use whenever if you have AMS or ACSM in your lab, or if you have seen somewhere, you will always see that people tend to tell you that we calibrate with ammonium nitrate, not with ammonium sulfate. People usually calculate with ammonium sulfate as well, but later part, but primarily with the ammonium nitrate, because it has higher efficiency in terms of ionization, in terms of vaporization. Okay. So for the ionization calculation, so the curve looks like this way. So you have your signal from the AMS, you have your mass that you have sent to calibrate the instrument. So this is the known one that we are sending it through nebulizer and detecting it through CPC. Okay, so this will basically give you particle size and mass information. This is basically the instrument response. So the slope of this will give you the ionization efficiency. So that will be using it for the calibration of AMS instruments. Okay. And for the size scale, we basically do this the response of this velocity is basically time of flight. Okay, so we term it as velocity. So we tend to see for different sizes how this time of flight varies and try to establish a relation and try to fit that same relationship into your instrument so that your size calibration will always be proper and needs to be tuned in in a successive time interval. So I won't be going into details of this. So this will be all will be explained in tomorrow's your visit. So I just want to highlight one point. So here actually we always try to see this air beam connection, air beam concentration. We'll always try to see that. So this air beam is basically a measure of how your aerosol particles are reaching from your inlet to your detector. Okay. So for that, we mostly try to use NBISET 28. So do you know, this is like a very basic thing. So do you know why we use NBISET 28 for a measure of air beam? So any guess? So for which compound is NBISET 28 nitrogen? So what is the abundance of nitrogen in atmosphere? It's 78%. So it's maximum. Okay, so that's why we tend to follow this NBISET 28 as major signal for your air. Okay, ambient air. So now I'll come into the how these AMS datasets can be used to calculate the aerosol hygroscopicity. Okay, so there are we mostly use this ZSR relation in order to calculate hygroscopicity from your AMS datasets because you are getting organics and inorganic concentrations. So this kappa can be a linear combination of these individual hygroscopicities. Okay. So if you see here, so there is this epsilon term is basically your mass fraction, or it can be a volume fraction of your different aerosol species, and kappa is the individual hygroscopicity. So how we will know? For inorganics, it's fairly simple. So kappas are already studied vastly, and you know all these values as this one. Okay. But for the organics, you don't know its exact value. People tend to consider this kappa as 0.1. Okay. But it can vary from 0.1 to 0.3 depending on your chemical composition or the extent of sources that are available at your observation site. Okay. So if it is a traffic dominant, so this value will tend to go below that. If it's mostly driven by your long range transport, or say photochemically very active site, then your kappa will tend to go higher. Okay. So if it's a fog processing, so your kappa will be around 0.3. Okay. So for Delhi, it can be very high and it will be varying fastly. Okay. So now in atmosphere, when aerosols are present, so they are not directly present as a individual entities. Okay. So if your aerosols are freshly emitted, so it will be always in external mode, externally mixed mode. So because of that only, if you remember, actually we got different kind of modes of growth in STDMS cap. Okay. So if it's externally mixed, what does it mean? It means all the individual aerosol particles are having unique properties. So their properties are being retained. So when the particles are internally mixed, so they have ion exchanges. Okay. So their properties are diluted now. So they will have a bulk property. Okay. So if the aerosol particles are internally mixed, then it is fairly simple to calculate the kappa. If you have externally mixed aerosols, which is the case mostly for your ambient aerosols, so the calculation of kappa becomes complex. So in order to calculate that, you have to consider ion pairing method, and you have to calculate for individual of species to ultimately determine kappa. Okay, you understood this point, right? Okay. So this internally mixed aerosols can come when you have in your observation site, you have more influence of long range transport. So there will be a lot of photochemical transformations, aging, in cloud, out cloud, scenarios. So that will lead to your aerosols to be internally mixed. But at the most of the time, aerosol particles are always externally mixed. Okay. Sticking to each other. Like suppose if you have dust and black carbon, so it will stick to each other from the outside. They won't be mixed together. Okay. Either they'll be in the form of coating or something else, but it won't be mixed. Okay. So there are some general things to remember actually. So like which I have already mentioned. So in general, actually, we consider hygroscopicity of organic aerosols as 0.1, but it cannot be 0.1 always. So it can vary depending on your sources, depending on your extent of aging. Okay. So for black carbon, what I have already mentioned, or for the organic aerosols that are being emitted from your traffic emissions, vehicles or combustion sources. So the kappa value is always tends to 0. So there is no hygroscopicity of those particles. Okay. So for inorganics, hygroscopicities are well defined. So you can always get some literature values. You will always get literature values of different inorganic compounds in the form of papers. And for organic aerosols, there are some derived ways to calculate kappa. Okay. So one of the ways estimating through fraction of 44. So 44 is basically CO2 plus. And if you tend to remember your 12th classes, so for carbon, the maximum oxidation state can be CO2. Okay. So it cannot go beyond CO2. Okay. So this CO2 plus can be considered as the maximum oxidation extent of carbon or hydrocarbons or any organic compounds that can be parameterized to calculate this kappa value. So this can also be a handy tool to indirectly calculate your organic aerosol instead of just assuming 0.1. Okay. And you should always have size resolved chemical composition, because if you are always trying to use a single kappa or a bulk chemical composition kappa, it will always tend to give you more uncertainties. So you always should have size resolved chemical informations. So in order to better predict your kappa and more closer to the realistic one. Okay. So there is a third way to calculate this hygroscopicity parameter. So I'll try to explain this CCN counter a little also. So have you heard about this CCN counter? How many of people you heard? So it measures potential cloud particles. Okay, so in the whole aerosol population. Okay. So what it basically does actually, it creates a supersaturation environment, that is also user defined, by setting up some different temperature gradients. Okay, so there are 3 temperature gradient points longitudinally, okay, or vertically. So you are setting up different temperature gradient, and based on that, you are creating a supersaturation environment inside an instrument or a column, and you are trying to make all the aerosol particles that are present in the atmosphere and give an environment to grow. Okay, and you are at the end of your chamber, you are trying to measure all the particle sizes as well as number using an optical particle counter, so which has a range of 0.75 to 10 micrometer. Okay, and it has a 20 size beams. So these are all technical informations. So and it has sampling frequency of 1 second. So in every 1 second, you can calculate CCN number concentration. So this is actually the schematic diagram of how this CCN counter works. So there is there are 2 wet valves where there are some porous materials from where there is a continuous flow of water, which is always creating a supersaturation environment. And you have different temperature set points here. Okay, so you have temperature gradient going higher from top to bottom. And you have to always remember that this is the sample line. So it's not like when you're setting up one supersaturation all the way here, starting from here to here, the supersaturation is that. Suppose if you're setting 0.3% supersaturation, that means 100.003. It's the actual convention of 0.3. So when you're setting up, suppose 0.3 supersaturation, it need not to be at this point, it is 0.3. So when the aerosol particles are going out of this chamber, at the end point, it will reach 0.3% supersaturation. Okay. And the main theory of this on which this CCN counter based is your mass flux of your water molecules are are traveling faster than your heat fluxes, because you have heated I think porous materials here which has different temperature gradients, and the temperature of these walls are higher than your center line. Okay, so if this is true, the mass flux and travels faster than your heat flux. So your mass flux, that is water flux or water vapor flux. That vapor flux can go faster towards your center line, that is the sample line, faster than your heat flux. So at the same time, suppose if you consider this point B and C, for point B, the temperature will always be higher than point C because the heat flux is lower than mass flux. That means B temperature at B is always higher than C, but the mass flux of this point B and C will always be equal, tend to be equal because of the higher extent of flux of water vapor masses. So for a certain temperature, your point C will always be more saturated as compared to your point B. Okay, and you will always have a moisture that are more available than the thermodynamically allowed moisture. Like for a certain temperature, you have a capacity to hold a moisture in your atmosphere. Okay, but when you create this kind of situation at point C, you will have more moisture that will tend to create your supersaturation, whatever you are setting up. Okay, and this supersaturation we can create from 0.1 to up to 2%. So that means 100.02 up to 100.001 to up to 100.02. It's very negligible, but it sounds like very huge. Okay, but so this is actually the flow diagram. Actually, you can follow. So I have just mostly explained. This is the most interesting part that I tried to explain here. And we also tend to do the calibrations of CCN using the similar kind of methodology. We pass this ammonium sulfate or any salts. Preferably, we use actually ammonium sulfate, pass it through aerosol generator, then dryer, then DMA. DMA is for size selecting. If you see here, actually, we have calculated percentage of activation. So activation is nothing but your CCN number divided by total aerosol number concentrations. So there is nothing else. Now you can consider this as CCN as well, because CN is your constant. Okay. So, and we'll be scanning with different sizes. Okay. And this is for, suppose for 0.3%, and we'll be doing for different temperature gradients. Okay. So from there, actually, what we can calculate, basically, we can calculate the D50. So D50 is defined as the diameter where you have 50% activation. Okay. So if you see here, if you just go, because there is no line, it's very difficult to imagine also. But the D50 here, it's basically around 140 nanometer. If you just make a line of it. Okay, so it will be around 140 nanometer. So your D50 will be dP here. Okay, so I am using the same Euler theory to estimate supersaturation from these curves. Okay, so generally in CCN, we don't measure supersaturation. We assume delta T, and from delta T, using this Euler curve and different size scanning, we try to estimate supersaturation. Then you have, for different set of delta T, you have different supersaturation. If you make a linear fitting, you will get a slope. So for each value of delta T, what will be the supersaturation? So accordingly, you can calculate supersaturation. Okay. So in CCN, we don't measure supersaturation, we measure delta T. Like we control delta T, and accordingly, we estimate what will be the supersaturation. It's an indirect way. Okay. So this is the software interface where you can see there's a different set of delta T. It is increasing, and your CCN concentrations are also increasing. Suppose if you have 0.1 supersaturation and you have 1% supersaturation, in which condition your CCN number concentration will be high? Can you tell? At higher supersaturation, because you have more moisture for smaller particles to grow. Okay. So in the same way, if you are increasing your delta T, that means you are increasing your supersaturation. Your number concentrations are going up. Okay. So all these things you will be seeing tomorrow again. So that's why I'm just quickly skipping. So there is a way to calculate this aerosol hygroscopicity from these CCN and SMPS informations. So SMPS is basically scanning mobility particle sizer and CCN. So what we can do actually, this is the, like, suppose this is a average size distribution of aerosols that are present in your atmosphere, and you have calculated CCN as well through CCN counter. So you know CCN concentration suppose as 2000 particles, and you have a size distribution where the total number concentration is 5000. Okay, so what you will do now, you have all the size informations, so you try to back integrate it. Okay, so back integrate from the highest sizes to the point where your number concentration of from SMPS goes equal to the number concentration you got from CCN counter. Okay, so that many particles has got activated, right? So the corresponding diameter will be a critical diameter. Okay, so that critical diameter again you can utilize here as DP. Okay, and you know supersaturation what you are setting up for CCN. You know that. You know all other parameters, so you can easily calculate kappa easily. But the drawback of that method is basically you are assuming whole size distribution, so you are missing with the size result kappa information. Okay, so the estimated hygroscopicity is always a bulk hygroscopicity. You are getting it for the as a whole aerosol. You are not getting for individual sizes. Okay, and the critical diameter estimation can always be uncertain because your size distribution, as like you will be seeing in demonstration as well as tomorrow also. So there are bins. Okay, so it may not be always that your CCN is always equal to your SMPS concentration exactly point by point. So there will be some up and down. Okay, so because of that, you will add more uncertainty to your DC, because these size distributions are made in terms of bins. Okay, not a instantaneous like 100, 101, 102. It will be like 100 nanometer. Then after that, maybe 110 nanometer. After that, maybe 115 nanometer. So your DC can be in between 110 to 115. But you didn't measure any SMPS, like any measurement of SMPS within that size range. Okay, so you are kind of like modulating this DC, and you are putting more uncertainty in DC calculation in that way. So the method is kind of like robust and crude, but it will give you eventually a like appreciable like estimation of kappa. Okay. So now I'll try to highlight some of the I'll highlight a little results from our lab. So if you see here, actually this yellow line is basically the actual measured hygroscopicity. And the background color plot, the fraction plot is basically for your chemical composition. If you see here closely, whenever you have high kappa, so kappa axis is this one, and this is the fraction axis. Okay, mass fraction axis. So we try to see how this chemical composition is related to kappa. So whether is there any one-to-one relation or it's a indirect relation. Okay. So if you see here, when the kappa is high, your inorganic chemical compositions are higher. So this up to this blue line, these are all inorganic composition. You can see here. So the blue is nitrate. This magenta is not visible. Its concentration is very less. Ammonium is orange, and red one is sulfate. So whenever you have inorganic concentrations more, you are getting higher kappa. Okay. So if you remember that earlier slide, I can show here. So if you see here, for different inorganic compounds, the kappa is very high. Okay, as compared to organics, it's just 0.1 for organics. Okay, so whenever you will be having higher inorganics, you will tend to see higher kappa. If you see here, actually there is a dip in kappa, which is associated with your higher organics. Same is in the case of here. So that what that means basically, so this organic fraction can very well modulate your kappa, and it is not necessary that always your high organic fraction will always be related to your lower kappa. It can act in other way as well. So we have found some observations for that also. So here actually in this slide, we try to compare like whatever I have like explained with all these slides. So we have tried to estimate kappa directly from H2DMA through internal and external mixing of like utilizing the chemical information from EMS and from CCN as a bulk kappa. Okay, so if you can see here actually, so this externally mixed and internally mixed kappa, that is like light blue and the deep blue one, always tend to overestimate as compared to the red one. So red one is the actual hygroscopicity. So even though you are putting so much effort to estimate kappa through indirect ways, you may not be able to get or to reach the actual kappa, which is available in your atmosphere, like which is present in your atmosphere. So either you will be underestimating, like if you are considering that kappa from CCN, it's always mostly underestimating, or it will overestimate in terms of chemical composition. So even though it's overestimating or underestimating, if you don't have any measurements of kappa, so this can be a best way possible to evaluate, estimate, and apply for your research purposes. Okay. With some pinch of salt, you have to consider. So this is another way just to show how this hygroscopicity can influence, or the size can influence your activation. So here actually we try to show the activation fraction. It's you can consider it as activation fraction, that is basically CCN divided by total number concentration. Okay. To geometric mean diameter. Have you heard about geometric mean diameter? So it's basically N means total number concentration root of individual sizes, okay, to the power of their number concentration. So it's basically give a fairly estimation of your mean size, because in that size distribution field, you cannot do a linear mean function, or you cannot use. You have to use a multiplication function in order to get this mean diameter. Okay, so that we term it as geometric mean diameter. So geometric mean diameter for different kind of aerosol size distributions. So when we try to compare this geometric mean diameter with activation fraction, so we try to see for a defined geometric mean diameter for a distribution, we have seen lower activation and higher activation as well. So when we try to see what may be the reason for different cases, like if you consider for case 1, case 2, case 3, case 4, so there are like geometric mean beams, that size beams, for which you have higher activation and lower activation as well for different cases. So when we try to compare for different cases, what we have found, so always lower activation cases are always associated with your higher organic fraction as well as your higher number concentration. So higher number concentration always tend to indicate that you have active sources like primary emissions, like biomass burning, be it biomass burning or any kind of traffic emissions. So that will tend to increase your number concentration as well as increase your organic fraction. So that will tend to decrease your hygroscopicity. So both number, size, and the chemical composition can influence your aerosol to CCN activation in this way. Okay. So these cases are all almost similar. You can see I won't be explaining all those. And just I tend to highlight this and finish my slide with this graph. So if you see here, actually we try to, so from this graph only, we try to segregate some of the points where you have similar size distribution. So the whole talk was based on whether size or chemical composition or hygroscopicity is influencing your aerosol to CCN activation or not. So here actually we tried to somehow fix the size. So how we have fixed the size? So we have checked for data points where size distributions are similar. If you see here, actually for this case and this case, size distributions are almost similar and the GMDs are also similar. Okay, so the GMD is a measure of your size distribution. So if you see here, actually both the size distributions are similar, but your activation, if you see, so for this, I think this blue one, if you can see here, actually blue one is the higher activation fraction and orange one is the associated with the low activation fraction. So even though the sizes are similar, there's a differentiation in terms of aerosol activation as well. Okay. So when we try to see in terms of chemical composition, whether it's a hygroscopicity effect or not, because sizes are similar. So there is no way that size can affect your activation fraction. Okay. So when we try to see that, we try to like what we found out basically, whenever you have higher organic aerosol contribution and low inorganic aerosol contribution, the activation fraction tends to go low. That means if you have higher population of organics and lower population of inorganics, your activation fraction from aerosol to CCN to cloud activation will be very low as compared to the opposite scenario when you have higher inorganic concentrations. So this slide can give you a feel that hygroscopicity is equally important in terms of aerosol to CCN activations, in addition to your size effects. Okay, so with this, I'll be closing my talk. If you have any questions, you can ask, or you can ask later as well. Oh.
Hello. Sir, can you open that slide in which you are finding the kappa using
Okay. Kappa using?
HDMI?
Okay.
Yeah, in the second formula, can you tell me what does that N1, N2 means?
So N1, N2 basically, suppose I'll just do one slide. So suppose if you see here, so you have two different modes, right? Here. Okay. So for one mode, there might be some number concentrations. For different second mode, there will be some associated number concentrations. So those N1 and N2 are basically corresponding to the number associated with these modes. Okay,
So
N1 and N2.
N1 is the number concentration
For
associated.
one mode. So there is two mode. If you fit Gaussian function, there will be one mode, then there will be another mode. Okay. So there will be number concentration associated with 1 and 2. There can be multiple one as well. Okay. You understood or?
I understood. Yeah.
Okay. So if you compare it here, so you have single Gaussian function. So all the number that are lies with these are all number concentrations. So it will be associated with the one mode. Okay. So when you are getting two modes, so there will be like one Gaussian function, another Gaussian function. It's basically fitting and getting the number concentrations out of it. So those N1 and N2 are basically the numbers for which you are getting that growth.
That peak.
That peak. So peak corresponds to the middle peak, points out your growth. Okay, growth factor. It will be the wet diameter. So wet diameter divided by dry diameter will be your growth. Okay.
Also, in the calculation,
Yes.
see, so there's this factor, growth factor Q minus 1. So suppose in the data, if the growth factor is less than 1, so the kappa value is negative.
Yes, yes.
So what does that exactly mean?
So like if you think ideally, so it cannot go beyond 1. It can be 0. Okay. So there is no growth. Okay. 0 meant like your dry diameter and your wet diameter can be equal. So the ratio will be 1 always. It can always go, kappa always go as 0 because there is no affinity towards your water vapor. Okay. But in principle, it should not go below 1, below 0, because you cannot decrease the size of your particle, considering all the instruments are working fine. Okay.
So we have to discard such values, right?
Yes, we have to discard. It's a kind of like imaginary situation where whatever dry particles you are putting, you are getting a lesser size wet particles. So that is not possible until unless you have a temperature related problem. Suppose if you're sending ammonium nitrate particles and in a way where you have higher temperature, so your particle size tend to decrease because of the evaporation due to temperature. Okay, so you will get a lesser size. So that is not a true situation, right? What you want to measure. Okay, so in no way it can go below, like the growth factor cannot go below 1.
Thank you.
Okay. Okay, we can discuss in.
Thank you, Subrata, for the lecture. We can discuss with Subrata during the break. Now we will take a break for tea. Please gather back by 12. by 12. Now I invite Dr. G. Pandidure, Project Director of Atmospheric Research Test Beds, IITM, to deliver third lecture of day 2.
Good morning, all of you. We had 2 long lectures. Anyway, I think still people have not come back after tea. Shall we start? Okay. I think today morning you got lectures on hygroscopicity and aerosol mass spectrometer for chemical composition. So in this lecture, I will cover aerosol cloud interactions. Yesterday, you saw lectures from Dr. Padma Kumari that how aerosols are influencing the climate directly. It's a direct effect because aerosols can scatter and absorb. It can reduce the incoming solar radiation reaching the Earth's surface. So in turn, it cools the surface. At the same time, it can also change the radiative energy budget at the top of the atmosphere. So this is a direct effect. So indirectly, aerosols also can influence the cloud microphysics. If there are more aerosols, there could be more cloud condensation nuclei. Subrata talked about how the aerosols gets activated into cloud droplet. So in turn, it can affect the cloud microphysics and also precipitation. Okay, yeah, it's okay. So these are the processes in the atmosphere the aerosols influence. For example, if you see, okay. Yeah. If you look at, there is primary aerosol production and there is a aerosol life cycle. There are chemical processes and aerosols have a wide spatial and temporal variability and complex chemical composition. So some of them act as a cloud condensation nuclei. Some of them even act as, very few act as ice nuclei. So it's a very complex aerosol cloud life cycles. In turn, it can alter the precipitation. Okay, so to understand these processes, we need to have a lot of measurements with advanced instrumentation. That's what we have been seeing last 2 days. So when we say aerosol cloud interactions or aerosol indirect effect, it is often used to convey these microphysical processes. The first one is the cloud albedo effect. Here, the higher aerosols, it means there will be higher cloud condensation nuclei. There will be higher cloud droplet number concentration. If there are more number of droplet concentration, the size of these drops could be smaller. So it can enhance the reflectivity of the cloud. So if you look at here, the volume is same, right? In both cases, the volume is same. But in one case, you have one droplet covering that volume, whereas in the other case, you have 5 droplets covering that volume. So here same volume, but the surface area is more. So it will increase the reflectivity of the cloud. This is called cloud albedo effect. In polluted environments, you can have more aerosols, so will lead to more cloud condensation nuclei, which will lead to more cloud droplet number concentration. So it will have more reflective surface area. The reflectivity of the cloud gets enhanced, right? So what it does is it cools the surface because more radiation gets reflected, it cools the surface. This is also called Tommy effect or albedo effect. So this is one good example for cloud reflectivity. If you look at this is a satellite picture. So these are ship emissions, ship tracks. So you can see that there is an enhancement of reflectivity, right? So this is what the more emissions will have particles, and in turn the reflectivity gets enhanced. Then the other second effect, indirect effect, is cloud lifetime effect. Here, if there are small droplets, it will lead to suppression of collision coalescence, and it will further delay the warm rain initiation. So here you can see if the droplet is big, sorry. So here in this case, you see the drops are big while falling. It can collide and coalesce with other drops, and the droplets, the probability of forming a bigger droplet is higher. Whereas if there are smaller droplets, it will just follow the streamlines, airflow streamlines, and it will bypass the falling drop. So here, what happens is the collision coalescence gets suppressed. If collision coalescence gets suppressed, means the larger droplets are not tending to form, so it will delay the warm rain initiation. So this is one of the IPCC report. If you see here, the all other this column, if you look at, this is the level of confidence. These are the radiative forcing by emissions and drivers. So if you look at the well mixed greenhouse gases, they have a very high level of understanding. Whereas when you come to aerosols, the direct effect, the direct radiative effect has high level of understanding, confidence, whereas the cloud aerosol interactions have low level of confidence. Okay, so that's why a lot of research is focused into understand how the aerosols are influencing the cloud and precipitation. So here, the anthropogenic emissions, if you look at which will lead to aerosols, not only anthropogenic emissions, even the direct, even the natural emissions also will put out a lot of aerosols. Some of them are, most of them are cloud condensation nuclei. Very few are ice, contribute to ice processes, and there are scattering type and absorbing type. So it can influence the radiation reaching at the surface. We call solar dimming. In a way, it counteracts the greenhouse warming at the surface, but in the atmosphere, depending on the nature of aerosols, if it is strongly absorbing, it can also warm the atmosphere. Okay, so there is a heating in the atmosphere, which will lead to change in circulation, and also it will lead to change in the climate. So to improve our understanding on aerosol cloud and precipitation interactions, so we need to enhance our knowledge on aerosol CCM and ice nucleating particle activation processes. I may call sometimes INP CCM, so make sure that you understand INP is ice nucleating particle, and what physical and chemical characteristics control the activation of aerosol to CCM. Subrata explained in the previous lecture, so how the aerosol's physical and chemical characteristics will influence the activation of aerosol into cloud condensation nuclei, and also what type of aerosols can serve as the ice nuclei. That also I'll try to cover. So in this area, I will talk about some of the IITM's initiatives for improving the understanding on aerosol cloud and precipitation. One such initiative about 15 years back, the experiment called KIPEX, which is Cloud Aerosol Interactions and Precipitation Enhancement Experiment. It is an aircraft-based observational campaign. The aircraft is fitted with the instruments for aerosol observations and cloud observations. So we go into different levels of clouds, and below the cloud base, how the aerosol behaves and what way the aerosols are affecting the cloud microphysics. That's an aircraft-based experiment. So the next initiative is the High Altitude Cloud Physics Laboratory. So there are advantages and disadvantages with the aircraft measurements. We cannot have several huge instruments into the aircraft. Also, we can fly for a few hours in the atmosphere using aircraft. So we cannot have a long-term data sets. Okay, so alternately, so we also established a High Altitude Cloud Physics Laboratory in Western Ghats at Mahabaleshwar, wherein you are going to visit tomorrow. So here, advantage is that we'll get clouds close to surface where the aerosols are emitted and how these aerosols can influence the cloud microphysics. We can simultaneously look at the measurements and infer how it is influencing. Also, we are also setting up atmospheric research test bed in core monsoon zone in central India, 50 kilometers from Bhopal city. So there also we set up all instrumentation facilities. So if some of you from near Madhya Pradesh, you can anytime visit, or you can plan to visit in later. So this experiment, aircraft experiment, the objective is to understand the aerosol cloud precipitation interactions and also to formulate a specific basis for rain enhancement. So this initiative is going on for last 15 years. And if you are interested in more details, you can talk to the project director, Dr. Tara Prabhaharan. So she's available in this institute. Then here, what I want to give you is that these are vertical profiles of cloud droplet size distribution observed in continental and maritime clouds. When I say, I think you are all familiar with now size distribution. Yesterday, Manish gave a brief outlook of how do we observe the aerosol size distribution, right? So size distribution is how many particles are there in a given size bin. Same way in the cloud, how many certain number of size droplets are there in certain size bin. So here, the cloud droplet size distributions are measured using an aircraft flying into different regions. So this region, what you are seeing left-hand side, is a continental clouds. The first distribution is taken at 4.5 kilometer, which is not possible with the ground-based measurements. We have to go into cloud with an instrumented aircraft, right? So this is a cloud drop size distribution obtained at 4.5 kilometer, and this is the cloud drop size distribution observed at 7.4 kilometer. So these are in meters. What you are seeing, the last 4 digits, they are in meters. Okay. So within this depth of 3 kilometers, the cloud drop size distribution did not broaden much, right? So whereas if you look at the other case, the first black one is about 800 meter. So this is a marine cloud over Mangalore, okay, in coastal region. So you have seen that around 800 kilometer, this is the cloud drop size distribution observed. And this color is at 3.3 kilometer. Same around 2.5 kilometer, here you can see the drop size distribution gets broadened. So what happens here is, as I said, the increased number of aerosols can lead to suppression of collision coalescence efficiency. So it led to a decrease of suppression of collision coalescence, whereas here the collision coalescence efficiency is very efficient. That's why the drop size distribution has broadened. So there is a likelihood of getting warm precipitation in this case. Whereas here, the warm precipitation will not come, whereas the cloud depths can go to deeper, and it can lead to ice microphysics. It can lead to a cold rain process. Okay, so that's the idea. So if you look at here, these are again drop size distribution observed with a imaging probe. Okay, so I will come to these probes later. So here, so what we observe here is you see some ice crystals here. So these are some of the ice crystals we can observe at above 6 kilometer. This is about 7.4 kilometer. This is about 6.5 kilometer. So this is in meters, and temperature is given here, and the vertical velocity also is given here. Okay, so what happens is that above 5 kilometer, so we tend to see the ice phase cloud, and dust is acting as a potential ice nuclei at temperatures lower than minus 14 degrees Celsius. So in pre-monsoon, you can see the dust concentrations are high in the atmosphere, which can lead to changes in cloud microphysics. It can suppress the warm rain initiation, but it can lead to ice processes or cold rain process. So now I mentioned about the aircraft experiments. You can really go into clouds with the instrumented aircraft. I will come to those probes later. But there are disadvantages that we cannot have all sort of measurements, like if you want to say hygroscopicity, growth factor, or chemical composition with the mass spectrometer, which are heavier instruments which cannot be taken in a small aircraft. We need to have a very big aircraft to have all sorts of measurements. So alternately, so what we explored is that we set up a huge observational facility where clouds come close to surface, and so you can measure at a longer time period. So if you look at our rainfall climatology from satellite data, you see that there is a huge rainfall in this region, Western Ghats. Okay, so it's mainly because of this orographic influence, because you have Western Ghats mountain, and the moist southwesterly winds will get obstructed by this mountain. Then there is a forced condensation. The clouds tend to grow up, okay, lift up, and then the warm rain microphysics gets very activated. You get higher rainfall here. So these are the objectives of high altitude cloud physics laboratory that we will be visiting tomorrow. This is to give an overview that these are all the measurement facilities available at Mahabaleshwar laboratory. On aerosols, and you have already, I think, covered by previous speakers on SMPS and aerodynamic particle sizer for coarser particle size distribution, and CCN counter to measure how many particles get activated as a cloud condensation nuclei at different supersaturation, and the nephelometer for scattering and absorption coefficient, and a multi-filter rotating shadow band radiometer to get the aerosol optical thickness, which is nothing but the integrated extinction coefficient. So I think you're all familiar with the extinction coefficient. Extinction is a sum of scattering and absorption. Okay, so then we also have sun sky radiometer, which also you will get to see. And so idea is that not only you measure the extinction from the direct solar radiation, we can also look at the sky at different scattering angles. So now that last 2 days, you may be seeing a very clear sky, the blue sky. Let us say that something, some lorry tires get burnt somewhere. So do you see such a very clean environment? So there are black particles Okay, then it becomes dark. Okay, so if you can measure sky brightness, then you can also estimate what fraction of this extinction is coming from absorption. Okay, so you can also able to derive so this extinction coefficient, how much is contributed from scattering and how much is contributed from absorption. Then coming to cloud, we have cloud probe, ice nuclei counter. So I think mainly I will cover these two today. And we also had deployed radars. So at present, you will not be able to see the radar here. But if you walk around the campus, one of the precipitation radar you can see here. So the other instruments are covered now, hygroscopicity, differential mobility analyzer. So VOC is not beyond the scope of this workshop. So these are all the different observing facilities set up at Mahabaleshwar. So I think I'll try to cover cloud probe. If time permits, I'll cover spectrometer for ice nuclei. So as he mentioned already, the CCN activation is mainly depends on the dry size of the particles and its chemical composition, and also hygroscopicity or its water uptake. For ice nuclei activation, the temperature, the temperature and the aerosol concentration and types. So this is one such result from our laboratory that you can see. The right panel shows the aerosol variation in a day. Okay, it's an average, seasonal average diurnal variation. If you look at here, this is the aerosol concentration in different seasons. You are seeing some different peaks, right? So in monsoon, you see a morning peak, then very small peak in the afternoon. Whereas in winter, you see there is a morning and afternoon peak almost equally dominant. Then in pre-monsoon, March, April, May, so you see the afternoon peak is dominant, but still you are seeing the two peaks, right? So it shows that there is a anthropogenic activities are playing, right? So in the late night or early morning hours, you have less concentration of aerosols. Then during the day, you are getting high aerosols. At the same time, the left panel shows the cloud condensation nuclei concentration at different supersaturations. So that also shows a similar pattern, right? If there is a low supersaturation, you have less CCN. If you give high supersaturation, here high means like a 1%. Again, supersaturation 1% means 101% relative humidity, right? So you are drawing the aerosols and exposing them to a certain supersaturation and counting them, how many particles got activated. If you take the ratio, if you conduct an experiment, Subrata was talking about activation fraction. Suppose let us say 1,000 particles were pushed into CCN counter. Then at the outside of CCN counter, if you are seeing, let us say 500. So then the 50% of the particles got activated as a cloud condensation nuclei. That is the activation fraction 0.5, right? So these are the variability. Then you try to understand why in pre-monsoon afternoon higher CCN is seen. Why in monsoon we have in the morning we see higher CCN. So these are all science questions. You have to explain with a source apportionment or what are the activities going on in that region, etc. So if you want to measure cloud drop size distribution, cloud microphysics, so you need to have some cloud probe. So these probes are based on optical principles. Okay, so you can see the scattering, and based on scattering, so you try to see size and its number. So here, this is a combination of two probes. So what you're seeing here is the two probes here. One is cloud droplet probe, which covers up to 50 micrometer. 3 micrometer to 50 micrometer. The other one is covering from 25 micrometer to about 150, sorry, about 250 micrometer. Okay, so you use two different probes. One is a optical probe. The other one is an imaging probe. I will come to that. So the working principle of these probes. Yeah, you have some question? Two curves are there. You mean? This one? Oh, okay. So if you observe, yeah, with the time if you observe, so the clouds are coming to your probe, right? The clouds are moving and you keep a probe like this. See, the probe is kept like this. So if the clouds are going in with different times, different types of cloud drop size distribution, you can observe. Okay. So with the time it is changing. That's what I want to give here. Right. So the cloud droplet size ranging from 3 micrometer, it can detect up to 50 micrometer. Depending on, suppose if you sometimes you get a larger droplets, so it senses that. If you see the combined with both the probes, because this can give up to 50 micrometer, the other one can start from up to 250 micrometer. You get a complete spectrum of cloud drop size distribution. If you integrate this, you will get the total number of cloud drop concentration, number concentration. Okay. So I'll come to this working principle of the cloud droplet probe. So as I said, it is a probe which can measure cloud drop number and size in the size range from 3 to 50 micrometer. It is a forward scattering optical spectrometer. So it can detect particles and it can sizes. So which pass through this laser beam. Okay, so it's based on forward scattering. So I hope you're all familiar with the forward scattering and backward scattering. Okay, so forward scattering, what do you mean? Suppose I'm putting a torch on you. Suppose, let's say I'm putting a torch on you. The light beam is coming towards you. So you are looking at in the forward direction. So that's the angle at which you are looking at. So you will get a forward scattering. Suppose I am putting a torch and I'm looking at from here. I'm looking at the backward scattering angle, right? So these probes, you see that the beam is going from here. The other side, you have a detector. So beam is focused on to detector. In between, if the cloud droplets are going, so you will be able to, based on scattered intensity, so you can size and then later size and put in different bins. Then if you integrate, you will get the total number concentration. So this is the principle, forward scattered light. Again, in the optical properties of aerosols, if you are, I hope you are familiar with the Rayleigh scattering and Mie scattering. So Rayleigh scattering is the particle size is, if the particle size is much smaller than the incident radiation wavelength, then what you see is a Rayleigh scattering. If the size is almost equivalent to the wavelength of the incident radiation, then what you see is the Mie scattering. Okay, so generally the molecular scattering is called isotropic scattering. It scatters uniformly in all directions. So whereas in Mie scattering, the scattering is very much angular dependent. There will be high intensity in the forward scattering angles, and there will be lower intensity in the backward scattering angles. Okay, so you're also familiar with LiDARs. So LiDAR sends a vertical beam like this, and the detector also is at the ground. So you are looking at the backscattered intensity. So the principle is that forward scattering. Again, the other parameter which you need for you can derive from this angular scattering properties. like asymmetry parameter. So if the scattering is uniform in all directions, then the asymmetry parameter is 0. Okay. If predominantly you get scattering in the forward direction, that you will get, if it is completely forward scattering, then it is +1. If it is completely back scattering, it is -1. So the asymmetry parameter can range from -1 to +1. Okay. So this is also one of the parameter derived from phase function of angular scattering intensity. Okay, so that is also required when you want to calculate the radiative transfer using these optical properties of aerosols. Not only the extinction coefficient, you also should know what is the pattern of scattering. You should know what is the asymmetry parameter. And also there is I already mentioned that what part of extinction is contributed by absorption. So if the extinction is purely due to scattering, then we say that the single scattering albedo is 1. Understand? So if that is a fraction of scattering in the total extinction, let us say scattering divided by extinction, and extinction is scattering plus absorption. You put absorption 0, then it is leading to scattering by scattering, and the single scattering albedo is 1. If the absorption increases, the denominator increases, the single scattering albedo will get reduced. For example, sulfate aerosols will have single scattering albedo 1, and the carbonaceous black carbon aerosols can have 0.2. Okay. Then there is another probe which we use for larger particles. Same probe is used in aircraft also. Only difference is that in aircraft you can fit that probe directly, whereas in ground you have to slightly modify, because in aircraft you are going with a known speed. You will record the speed and all airflow is known. Whereas in the ground you need to set up an aspirator, and you should know the flow of the air. Okay, you are drawing the cloud air mass into this scattering volume. Okay, this is a aspirator unit, so it will draw the cloud air through the probe. Yeah, so imaging probe, the name itself says that, so it just images, right? It just captures the shadows of the particles. Let us say this probe is taken into ice, supercooled or ice cloud. So there will be crystals, ice crystals like star type, what I shown here earlier. So that will be the shadow images you will see, right? So then you can both count and also understand what type of ice crystals were there. So this has a linear array of 64 photodetectors. So that's how whenever some crystal is passing through, you will get a shadow image of that ice crystal. So from that you can count the ice crystal concentration and its shape. So to check whether these instruments are working properly, so we also need to calibrate and see so whether what size of cloud droplet we observe is correct or not. So for that we need to do calibration of this cloud droplet probe. So for that we use glass beads of known size. So here this the glass beads of known size is given here. So which is inserted into this scattering volume. So then you will see, so what you observe in the your probe output. So what kind of droplet sizes you are observing. So because we are using the glass beads, whereas glass bead size and the water sizes may not be same, right? So it will have different values. So it has to be calibrated that if from these histogram that we'll be able to calibrate. Okay, we have known size of glass bead is introduced. So what kind of size distribution we are getting, sizes we are getting. Same way for imaging probe also in the volume. So we need to introduce a spinning disk. So you can see here there is a spinning disk which has some images, known images of different sizes, 50 micrometer to 500 micrometer with known sizes. You introduce that in this field of view and start recording it. Then whether you will know whether when I introduce 50 micrometer, the instrument should also give us the same size. Otherwise, we need to adjust that. We need to calibrate. Okay, if there is a drift, so we need to take it into account. So this is how the imaging probes are calibrated. Now, suppose you want to understand the aerosol cloud interactions. You are trying to see simultaneously, you are measuring the aerosol concentration and cloud droplet number concentration, how it varies with the time. Okay, so this will give you to get an idea. You can estimate the aerosol cloud interactions. So what you see here, aerosol cloud interactions, it is relative changes. Let us leave this equation so you can see from here. So aerosol cloud interactions in terms of number concentration. So here, the relative changes in aerosol proxy. So here alpha is CCN proxy. Okay, you can suppose somebody want to use satellite data, he can use alpha as aerosol optical thickness. So it's a general equation. So in this case, if you have aerosol number concentration and if you have cloud droplet number concentration, D is N suffix D is the droplet number concentration. And so if you see that if there is an increase in aerosol number concentration, there should be increase in droplet number concentration also, right? So it is proportional to that. So if everything gets activated, all aerosols are getting activated and the aerosol cloud interaction here is 1. Let's say 1000 particles are there, all got activated. So this is how with the number concentration you can derive, or with the size if you derive. So in this case, this is for a given liquid water content. What is the relative changes in droplet effective radius? Yesterday, they talked about the effective radius. If you know the drop size distribution, so you can also calculate the effective radius of the drop size distribution. It's the ratio between third moment and second moment. So if you look at the relative changes in droplet effective radius, so with the relative changes in aerosol concentration or CCN concentration, you can take. So in this case, but condition is that the liquid water content has to be same for cloud. Okay. Idea is that, see, if in a family, if the food quantity is fixed, okay, let us say more children are there, so they are getting less amount of food, and their growth also will be equally less as compared to all food is available to one kid. Okay, so this is how here, if for a given liquid water content, if the droplet number concentration gets enhanced, in the effective diameter of the droplets gets reduced. So whereas the CCN concentration and droplet number concentration can get enhanced, so through which you can estimate aerosol cloud interaction observationally. So you can utilize even the satellite data. For aerosols, you can use aerosol optical depth. For cloud, you can use cloud droplet number or cloud drop effective radius, and you can estimate. But you have to group the clouds having similar liquid water content. As I mentioned that there are two different methods with a number or with the droplet size, but it need not be same. The values need not be same. That we notice that. So if you estimate the indirect effect through both the number and size, there are some discrepancies, which mainly because the cloud condensation nuclei increases, the dispersion of the distribution also gets altered. So that's how, if we are able to correct that, then maybe the indirect effect estimates will be similar. So these are some of the results from our laboratory. Anyway, I think I don't have to cover this. Then briefly, I'll cover for another 5 minutes the ice nucleating particle measurements and its parameterization. So the INPs are very small set of atmospheric aerosol, which helps in the formation of ice particles. It is very, very less as compared to cloud condensation nuclei. For example, 1 in a million of aerosol particles can activate as an ice nuclei. So most of the studies done across the world is using offline sampling and take it to cloud chamber and analyze. So here I will present some continuous flow diffusion chamber so that you can measure real time. It is similar to what Subrata has taken in the previous lecture for CCM chamber. That's also continuous flow diffusion chamber. So why do we need to understand these ice nuclei particles? Because they are in just one or two in a million number of particles. So it has impact on precipitation process, and also it can influence the radiation budget. So at present, the data is very limited. So hence there is a need for more ice nucleating particle measurements and monitoring. So the potential sources of ice nucleating particles are mineral dust emitted from deserts, then the aerosols with the biogenic origin from ocean surfaces, then the bioaerosols and organic aerosols from forests, then industry and biomass burning, the soot particles emitted from industry and biomass burning. So there are different nucleation modes through which ice crystals can form. For example, homogeneous nucleation, I think, needs very high ice supersaturation, which is not possible in the atmosphere generally. But there are other modes of ice nucleation, which is the first one. What you see is a deposition nucleation, so which is water vapor is directly deposited onto the ice nucleating particle. Then condensation freezing is water condenses on INP to form a supercooled droplet. Then it freezes subsequently. Then the contact freezing is, so if a freezing supercooled droplet comes in contact with the INP, so there could be a contact freezing. Then immersion freezing is INP become immersed inside a supercooled cloud droplet, and subsequently it gets frozen. So the effect of ice nuclei is that if you look at here, if there are two ice nuclei, the mid-level clouds will persist as a liquid. So the net climate effect is cooling. So whereas at higher heights, cirrus form at highest, and whereas if there are more ice nuclei, you can say fewer and larger cirrus ice particles, and there could be more extensive cold clouds. So these are the effect of ice nuclei from various possible sources. So this is the ice nuclei counter you will be seeing in the Mahabaleshwar laboratory. It's called a spin spectrometer for ice nuclei measurements. The challenges is that for ice nuclei measurements are the onset condition for various ice nuclei at different nucleation modes are not very well defined. So I think I can skip this. The early methods are where the sample air is cooled by sudden expansion to create supersaturation. That's how in cloud chamber they started measuring the ice nucleating particles. Later they used to collect aerosol samples on membrane filters. Then the filters are exposed to freezing temperatures and supersaturation inside diffusion chamber to identify ice nucleating particles. So recently the continuous flow diffusion chamber is widely used, which you will be seeing tomorrow. These are some of the previous studies, mainly from the offline sampling through printers. So this is how the summary of INP concentration and sources. There are several studies worldwide and how it varies with the temperature. You can see here. They have grouped into different types of sources. The particles emanated from sources. So some gap areas is that through offline samples, only deposition mode ice nucleating particles are measured. Whereas the heterogeneous ice nucleation is not very well formulated. So this is the ice chamber, wherein the ice supersaturation is set up. So what you see here is the wall temperature. Okay, one wall is warm wall, then the other one is a cold wall. The temperature range you can see from -40 to -30. So here is what that aerosol laminar flow will be there. Okay, so here you have so through which the aerosol samples will go, and you can get how many particles get nucleated, because you are giving a very high supersaturation. So at the end of this chamber, we have an evaporation section. So what happens if it is only water drops in the evaporation section, it will get evaporated. If it is ice crystal, so still it will remain. So based on the polarimetry and size of the particles, so we can count that, okay, it's really ice particles. Okay, so that's how the ice nucleating particles are measured. So we have to set this chamber for saturation vapor pressure for ice. So this is a detector. It has a polarization optical OPC. So based on the polarization, we can see that the ice particles will not be a spherical shape, right? So you can also identify through polarization. This is the ice particle. So to conduct the experiment, we need to also see the background frost concentration once the chamber is iced with 1 millimeter of thickness. So then also you see, look at what is the background concentration. There could be impurities in the air, which also can activate as a ice nuclei, which needs to be removed when we are looking at. So this is the evaporator section. So wherein you will see when they are not ice crystals, so they will shrink. They will shrink, and only the ice crystals will only get growth because of Furger and Findison process. Yeah, I'll skip this. So what you notice is here, so here the ice nucleation starts forming, right? So you start seeing the ice nucleation. Then again you ramp it to the experiment is conducted sequentially. Like I'll show you. First, you measure the background concentration and actual sample measurements. Periodically, routinely, you do that alternately, one by one. So before conducting the experiment, we need to check the dew point of the entire chamber. Then you pre-cool the chamber, allow the water to pass through, and then you are having a supersaturation. So a thin sheet of ice will form across the walls. Okay, so for that we need to use a millipore type deionized, distilled deionized water, so that there are no impurities in that water. Okay, so this is to collect the background concentration. So once the chamber is iced, so you will see there will be some certain number of background ice concentration. Now that chamber is ready for conducting experiments. So what you can do is you can do it in two ways. keep the chamber at a desired temperature and supersaturation condition and continuously measure the ice nucleating particle concentration, or you can also change the supersaturation by changing the temperature gradient. You will ramp the supersaturation, and at different temperatures, you can measure the ice nucleation. As I said, the cutoff and polarimetric detector will give you whether you identified ice particles or only droplets. So these are the sequence so these are some background concentration. Then you measure ice nucleating concentration. Again, the experiment will last for several hours. Okay, so it's not like a CCN counter. You can leave it for continuous operation. So the experiment has to be conducted by ramping, by checking the background concentration. So it's not a real-time measurements. Okay. I think I'll stop here. These are some of the measurements, and we try to use how these measurements can be used as a parameterization so that the modeling community can utilize this. So these are some of the papers you can refer. So to summarize, I think we have a lot of processes happening in the atmosphere, even if you consider a single grid box. So we need to consider several lot of processes. For that, we need measurements, which need instrumentation. So which has to cover from size, optical characteristics, mobility, all these. Okay. So this is how I'll stop here and take some questions. I think we're already delayed for time. Any questions? Yes.
So, which type of aerosols have higher efficacy to convert into CCN, like considering broad aerosol types like inorganic, organic, black carbon, and dust? And is this different for liquid clouds and ice clouds?
Yeah. So I think Subrata mentioned about the hygroscopicity, which is very high for inorganic aerosols. So inorganic aerosols can have more affinity with the water. So it can grow with the water vapor as compared to organic aerosols, which have less efficient cloud condensation nuclei. For ice nuclei, mainly the mineral aerosols and biological aerosols have higher affinity, or it can activate as ice nuclei.
So for ice clouds, does it depend on the size also? As for ice clouds, we need higher altitude, higher size will not reach at the higher altitudes because of the weight. So it will be smaller particles that will convert into ice.
Yeah, it need not be all from surface emissions need not go all the way there. With the convection, it can go. Still, there are transport of aerosols, aerosol transport, which brings the aerosols at even at higher altitudes, larger size particles. Larger size need not be above 1 micrometer. Even 1 micrometer size is large enough for dust particles can act as a ice nuclei.
Similar thing we have seen on the hydroplane kilometer by the ice of the radar observation.
Okay. Yes. Yeah, there are studies showing the elevated aerosol layers, and with the convection in summer, the particles are even going up to stratosphere.
Thank you for the informative talk, sir. So I have a question about that. From this study, can we predict the thunderstorm or lightning? That on which parameters we can predict this?
From this study, we cannot predict, but yeah, but if you can understand the ice clouds, then we will be able to give information on thunderstorm probability, because ice clouds only are responsible for lightning and thunder activity. But from these studies alone, we cannot say. So we need to measure other electrical properties, but we cannot say do it at the surface.
Thank you.
Yes.
During the interaction process, can we implement some cell structure model or such theory like the aerosols and the water vapors are overlapping it? Can we implement some cell structure model or theory something?
I'm not very familiar on cell structure. I didn't get the question exactly.
Means while we are studying the interaction, the aerosols and the droplets, while the formation process of the droplets. So, sir, can we implement the cell structure like the considering that aerosols, the water vapors are?
Yeah, actually, it's a nucleation. It's a nucleation,
Yeah.
so it acts as a nuclei either for a cloud condensation or for ice nucleation. So it is like a particle acts as a nuclei.
Yes, sir. So, means, if we are starting to study about the optical properties, so we will have some different optical properties for the aerosol part as well as for the vapor part. So, using a cell structure model, can we differentiate that?
No, for vapor, I don't know how do we get the optical properties, like a scattering. So,
Thank you, sir, for the lecture. If any further questions, discuss during the day. We'll break for lunch now, requesting everyone to gather back at 2 p.m. same venue for the hands-on session.